I'm very happy that Professor Gennaro Miller, the director of the Department of Physics, has come today to give his greetings to the community. Thank you, Gaetano, and all the other answers. I'm particularly pleased, first of all, I want to bring you the greetings of our community and the physics community in Naples. I will say a few words about our department, and particularly at least because we are in a place one across two academies, very ancient one. We are talking about the foundation about 15th century, ancient and important place where to discuss about science. So, and as I was saying, our department is a quite huge one, with respect to the size of Italy, of course. So it's over 200 scientists, 200 staff members in the department, with an extremely wide range of physics activities, from, of course, of experimental. Very active, and the event of today, which is just testimony this kind of activity, and I really welcome something like this opportunity. It is for me a synergic way to put together mathematicians and physicists. So I really appreciate this kind of activity, and I welcome you, and I wish you a very good job. Thank you very much.
Welcome to this morning session. My name is Howl, the project leader at the Institute of Quantum Technologies of the German Aerospace Center in Milan, and I will be chairing of the gravitational field with quantum, as well as proposals for measurements of even quantum aspects of the gravitational field itself. First speaker, we're pleased to have here Richard Howl from the University of London. He's going to tell us about tabletop experiments of quantum or tabletop tests of quantum gravity, so entanglement and beyond. So Richard, the floor is yours.
Is that okay? Yeah. Okay. So yeah, thanks Albert, and I'd like to say thank you to all the organisers for such a fantastic conference in a beautiful city, and also for changing the room, which is extremely great. So I'm going to be talking about tabletop tests of gravity, with a slight focus on looking at. Actually, maybe I'll switch to this one, because it's difficult to move around. Can Can you hear me at all? No? Yeah, I pressed it, but yeah, okay. Is that better? Yeah, okay. All right, so yes, I'm going to be talking about tabletop tests of quantum gravity with a slight focus on looking at alternative methods to testing quantum gravity away from those based on entanglement. Okay, so this was actually a done by members of the RQI North action to be taught at this conference. I should also say thank you to whoever it was who proposed this topic and all of those who voted for it and the organisers for choosing me to deliver it. Okay, so we can start with a brief outline of the talk, okay, which is going to follow the history of tabletop tests. Okay, also made a little bit in. Okay, so first we're going to start with the creation, okay, the creation of the idea. Then we'll move on to the classical age, okay, so that's the classical technology age of these experiments. Then we have the dark ages, this is the age of no ideas, this will be quite brief. And then we have Renaissance, okay, which is a rediscovery of the idea. Then we have the quantum technological revolution. Then we have explorations looking at exploring ideas beyond entanglement. And then finally, we'll discuss about judgment day, okay, when we'll find out if we have quantum or classical gravity. Okay, so I'm going to start with the creator, okay, which I think most of us know is Richard Feynman. Okay, because he was the first person who came up with this whole idea of testing the nature of gravity in the tabletop experiments. And he did this at the famous 1957 Schützhold conference, okay, where he spoke about take a small object, put it in a superposition spin, so like an electron, they then send it for a Stern-Gerlach experiment, then somehow connect this to a larger mass. It doesn't say exactly how, but the idea was that this then amplifies the effect, so you get the superposition of mass in two locations, okay, so these circles stick up and down. So then he talked about if gravity is quantum, then the gravitational field of the object should go into a quantum superposition. Okay, so the quantum superposition branch will be sourced up there or down there. Then he introduces another mass, okay, so let's put it on the right, and how this will feel the gravitational field of the object in a different position, okay, moving it in a different direction, and depending on the superposition branch. Okay, so there's been some papers that suggested that he didn't include such a mass, but if you look at the notes of the conference, he definitely does do that. But what's not perhaps 100% clear is what state this mass is in. Was it also in a quantum superposition to start with? But I think from the notes, I guess it wasn't, so that's what I'm going to assume. Okay, so then we have a superposition branch of the left mass moving up and the right mass moving up with it, and the left mass moving down and the right mass moving down with it. Okay, so Feynman never explicitly says this, and I'm not sure we really have this in mind, but today we would see that the full system is becoming entangled. And this was made explicitly clear by those collaborators, Carney and Bengal, many years later, which I'll come back to later in the talk. Okay, so if we have quantum field gravity, we seem to have entanglement, but if gravity were classical, then Feynman argues that gravitational field would not be able to be in a quantum superposition by definition, and so this right mass would not feel a superposition of gravitational fields anymore. So there's no way that it can enter into a superposition branch with this mass. Okay, so it seems like the system is separable to classical gravity. We don't get to entanglement. And before I have lots of questions on that, I will come back to some caveats later in the talk. Okay, but for now let's consider like a very simple example. This would be semi-classical Einstein gravity, semi-classical general relativity, which is supposed to be a fundamental classical gravity theory, where the gravitational field, the classical one, is sourced by the expectation of the stress energy matter, stress energy tensor matter. Okay, so in this case, we would naturally expect this white mass to just move towards the center of the two superposed states. Okay, so then we would have a separable state and no entanglement. Okay, so then with quite, what seems like quite a simple idea, it's going to be a quite simple experiment. Now, remarkably, we could potentially see quantum effects of gravity in the lab. And now with the advent of quantum technology, there's much effort going on in many different institutes around the world trying to make this sort of experiment a reality. But actually, arguably, you could say that the version of this experiment was performed over 40 years ago, and it was just classical technology. Okay, so this is the famous 1981 H-gamma experiment, okay, which is kind of like Feynman's, but rather than having this single progress on the right, now we replace that with two progresses at the end of the torsion balance. And quite importantly, we assume that quantum mechanics contains many worlds of simulation. So we have no wave function. We also have to throw another famous experiment into this, because this radioactive material in the experiment, and rather than putting the cat into the position of dead and alive, instead, this is meant to place the experimenters, on page, into a superposition branch of placing two large source masses in this position A, so this is looking from above, and also superposition branch of placing them in B, so this is like our source mass on the left in Feynman's experiment. So it's a bit more complicated than this, but it's kind of like if Don Page was to see radioactive decay, he places the masses in this position A, and if not, then he places them in position B. Okay, so then if we have Everettian quantum gravity, many worlds quantum gravity, which was of much interest in the 70s and the 80s, then we would have a globally entangled state. Okay, we have a superposition branch of Don Page placing the masses in A, and the torsion balance rotating to their gravity and rotating clockwise, and a superposition branch where he places them in B, and the balance goes anti-clockwise. Okay, so it's entangled. So that means that when Don Page looks at the rotation of the balance, he should find exact correlation between where he placed the masses and the rotation of the balance. Okay, but if gravity were classical, then, as we said before, there cannot be a quantum superposition of gravitational fields. That's our definition, at least. And so there won't be an entangled state anymore, and so there won't be exact correlation between the masses and the rotation of the balance. Okay, so for example, in semi-classical Einstein gravity, where now we take the expectation over the global wave function, then actually we wouldn't expect the balance to move at all, okay, because it's like all the effects cancel each other out, all the masses are there at the same time, okay, so the balance doesn't move. All right, so of course, you know, they did see exact correlation when they carried out the experiments, okay, so seemingly ruling out classical gravity. Okay, so then what's all this fuss about trying to make Feynman's experiments in the lab? Well, of course, you know, although this was an ingenious experiment, there are some major assumptions, of course, that go into it. Okay, so one that isn't spoken about very much is that, in a way, we have to assume that Don Page is trustworthy. Maybe he is, but there's no way of actually us knowing that by knowing that he does exactly what he's supposed to do in each superposition branch of the universe. Perhaps more importantly, it's only testing specific versions of classical gravity, those based on Everettian quantum mechanics. But you could have something, well, it's kind of so then showing that, if you believe in many worlds, quantum mechanics, then it's very difficult for you then to believe in a fundamentally classical gravity. But you could have something different, so you could have something like semi-classical Einstein gravity with the expectation not over the global wave function, or you could have things like stochastic gravity pioneered by Gubitosi and more recently explored by Oppenheim. And these are post-quantum theories, so they're not based on Everettian, and so they won't go with this test. So there are then strong reasons still to carry out Feynman's experiments beyond this many worlds interpretation. Okay, so now we move on to the dark ages, okay, where there's no ideas. Okay, but then a renaissance in 2010 because the Max Planck Institute republishes the notes on the Chapel Hill conference to now a broad audience. And of course, at the same time, we also have quantum technology. Okay, so that then brings me back to entanglement. So I said that in Feynman's experiments and Page-Garker's, entanglement is essentially the signature that is providing evidence of quantum gravity. But as far as I'm aware, that wasn't explicitly mentioned until after the republication of these Chapel Hill conference notes. Okay, so I think the first maybe to do this were Caffrey and Taylor, who proposed another fantastic Cavendish-like experiment. Okay, so like Page-Garker's with torsion balance, but now back to Feynman's original thinking that we don't need to include the observers in the superposition. So they then later connected this with the fact in quantum information you have local operations and classical communication. LOCC cannot create entanglement. So then if we assume that classical gravity is LOCC, and I'll come back to some caveats on that later on, then it can't create entanglement. Okay, but then really a revolution occurred with a paper by Sagata Bose and his collaborators and another by Chiaramonetto and Vlatko-Vedral that remarkably appeared at the same time. So in Sagata's paper, they talk about how you could make something like Feynman's original idea now into an experimental reality. Okay, so now they replaced that small object that had a spin with the mass itself and give it a spin. So this could be a diamond with an NV center. And they just send these through the Stern-Gerlach experiments to create your superposition of two locations. So no need for these mysterious interconnections that Feynman spoke about. They also introduce reverse Stern-Gerlachs, which Feynman also spoke about in the conference. And this then nicely just puts the entanglement between the spin degrees of freedom at the end of the experiments. As we can see, they also put the probe mass into a superposition of two locations. Okay, and that significantly enhances the effects because it's like quantum metrology. Now you're putting the probe state into a Newton state. And that means you can have much smaller masses than the Planck mass, which is what Feynman originally alluded to. Okay, and then if the superposition size is very large, then we find that the entanglement essentially scales as just the relative phase between the two closest branches, which goes as the Newtonian gravitational potential. Okay, and then we get maximum entanglement when phi is equal to pi, and that sets your values for the experiment. Okay, they also give a nice, well, a simple argument for why relativity could tell you that classical gravity should be LOCC. Okay, so the idea here is that in this case, the gravitational field should interact independently and locally with each mass, and then mediate the interaction as classical communication. So in Chiaramonetto and Vlatko-Vedral's paper, they also introduce similar experiments, but actually they argued that entanglement as a signature of quantum gravity is more general than just classical gravity being LOCC. And I'll come back to that. Okay, so then after these two papers, there really was an explosion of interest in gravitationally induced entanglement, with many more ideas on how you could look for this in experiments, many more ideas than I could possibly go through, but I will just go through one and two important ones. Okay, so one of these is a paper by Cristando and collaborators, where they showed that you could also look for gravitationally induced entanglement between two macroscopic oscillators. So again, like Feynman's experiments, but now you kind of do the opposite to Bose and Vedral. Now, rather than putting both masses in the superposition of locations, now you put neither in the superposition of two locations. But instead, they have to be in highly quantum states, such as states where the wave function is highly spread out. So now it's kind of like you have a continuous spread of superpositions, or it could also be momentum. More recently, there's kind of been ideas that, in a way, combine these two approaches by coupling the trap masses to qubits. So, for example, Lorenzo spoke about a fantastic idea yesterday of how you could couple qubits to trap masses and use inverted traps, which has recently been performed in Vienna to create Schrödinger cat-like states and reduce the time of the experiment to make this more feasible. There have also been ideas on how isolated microsolids. So for example, looking at the gravitational interaction between two large mirrors in an optical mechanical setup. And I think Honor will talk about his experiment towards this later today. Also ideas on using cold atoms. So for example, we recently looked at how if you had two atom interferometers next to each other and you had enough atoms going through them, then you would find that they also entangle due to their gravitational interaction. Okay, so showing that Feynman's idea is more general than just using things like solids. It can also be applied to other systems like gases. Okay, so hopefully that sounds somewhat exciting, and maybe it also sounds quite promising. But then you might be asking, well, why haven't we seen these experiments in the last 10 years? Well, although quantum technology has brought us closer, still the challenges remain substantial. Okay, so to give you an idea on that, the mass that we need to put in a superposition of two locations in the Stern-Gerlach experiment, well, that's about 9 orders of magnitude greater than the largest mass we've currently put in a superposition. And actually, that was using a very different system, using cold molecules in Vienna. If we were to look at the trapped microsolids, then here you need highly quantum states, for example, highly squeezed states, and we haven't seen quantum squeezing in such systems yet. And there are also many orders of magnitude greater than the best systems for squeezing at the moment, which I think are cold atoms. So the cold atoms experiments, you might be able to get closer on the squeezing, but now you need to really push up the number of atoms. So always in all these experiments, there's always places where you need massive improvements over the current state of the art. Also, just looking for entanglements in these microsolids is going to be a challenging process because this is a non-local measurement. And also, as well as experimental challenges, there have also been some theoretical questions on how much entanglement really is a test of quantum gravity, which I'll come back to. So while advances in theory and experiments might help with answering some of these concerns, I think this also motivates looking for alternative ways to test quantum gravity, beyond entanglement. Okay, so now we're going to talk about something completely different. Okay, now we're going to talk about going beyond entanglement. Okay, and as a first example, I'm going to talk about something that I think really nicely illustrates how you could do this. Okay, so this is a paper published last year, where essentially they talk about how, they point out that the set of non-LOCC channels is greater than the set of entangling channels in quantum information. Okay, so then if we assume again that classical gravity is LOCC, that suggests that there should be signatures other than entanglement that could provide evidence of quantum gravity. Okay, and they illustrate this with a particular example. Okay, so this is the experiment, the Cristando experiment, where we have trapped oscillators, as I spoke about before. And in the Newtonian regime of this experiment, it can be described by just this interaction Hamiltonian, which can be well approximated by well-known operations in quantum optics, beam splitting and two-mode squeezing operations. And in realistic experiments, we'd expect the gravitational interaction to be much, much weaker than the free evolution of the system. And whenever that happens in things like quantum optics, what you tend to do is you neglect the last two terms in what's called the rotating wave approximation. Okay, because these terms are highly oscillating, so you can neglect them on average, and you can see that, for example, in the interaction picture. Okay, but if we were to do that, and we assume that the oscillator starts off in vacuum or coherent states, then you'd find that you wouldn't get entanglement. Okay, it's well known in quantum optics that if you have a beam splitter, then you can't get entanglement from a classical input. But even so, if you just took this simple Hamiltonian and took some coherent states and let the system evolve, then at a certain period of time, you find that these states effectively get swapped. Okay, and a swap channel is known to not be an LOCC channel. Okay, so now we're getting something unexplainable by LOCC, and yet the system is not entangled. Okay, but they take this much further, and they derive a set of very nice LOCC inequalities with the idea that if violated, then in the experiment, then this would tell you that this has to be the non-LHC channel of quantum gravity. Okay, so they also talk about how you could look for this with just local measurements in an experiment, so no need for non-local measurements. And however, a set of numbers, you might be able to see something like an order of magnitude improvement over the time it takes for entanglements to be generated. And they also look at other experiments as well. Okay, so we can see then that with this ingenious alternative methods, we can potentially have an idea of how to test entanglement that's more general than test quantum gravity that's more general than entanglement, and also look for see experimental enhancements. Okay, so really then showing or illustrating the benefits of looking beyond entanglement. Okay, but I think we should also, to be fair to entanglement, consider if there are any difficulties with this approach. Okay, so for example, I said that you get this order of magnitude improvements over entanglement generation, but actually these numbers are in a fairly unrealistic regime of the experiment, so they're with huge times and very low trapping frequencies for such large masses, which is going to be difficult to achieve in actual experiments. So for entanglements, to overcome this, to use more realistic trapping frequencies and times, what you do is you go beyond coherent states. So you introduce something like highly squeezed states, and these are places where the rotating wave approximation is no longer a problem in generating a very large entanglement. And so it's an open question, I think, whether you still get benefits with this methods in these sorts of regimes. Okay, there's some other open questions that I don't have time to go through, but the one that I did want to concentrate a bit more on is how, because this is based on the idea that classical gravity is LHC, then any theoretical concerns related to that are also going to apply to this as well. Okay, so one of these is related to the fact that the experiments are operating in the Newtonian regime of quantum gravity. Okay, so the entanglement or the size of entanglement can be well approximated by just this interaction Hamiltonian for quantum gravity. So then the argument is that, well, we know that Newtonian gravity is non-local. Okay, so then surely LHC is always violated irrespective of whether gravity is quantum or classical, because interaction is always non-local. Okay. So that's one argument, and a counter-argument is that, well, we know that, well, okay, maybe the size of entanglement is well approximated by taking Newtonian gravity, but that's really just an approximation, and we know from other experiments that gravity, of course, is really relativistic. Okay, and so we can use input from other experiments potentially to say that LHC, the assumption of LHC can be justified. In fact, you can drop the Newtonian approximation entirely and rederive the effect using relativity. So for example, using linear quantum gravity, where we split the metric into a background and a perturbation, we quantize the perturbation. And you could do this in a path integral formalism, so that you're always working at the level of the action, okay, which means that it's a gauge-independent derivation. And I won't go through the details on this, but I'll tell you that if you do this, you can show that entanglement only occurs after a finite time in the experiments, as you might intuitively expect. So this is the time it takes for information about the position of the objects to propagate to one another through the gravitational field at the speed of light. Okay, so really illustrating the locality of linear gravity. But you could go further, and you could argue that, okay, maybe gravity is relativistic. We know that from other experiments. But while information may propagate through gravity at the speed of light, perhaps it's still non-local in the LHC sense, because we could have something like relativistic action at a distance gravity. Okay, so here essentially we're kind of thinking about gravity as a gravitational force again, but now it's kind of like a relativistic force where it takes time for one object to feel the force of the other through the speed of light. But now there's no mediating gravitational field, okay, so no independent gravitational system, as was assumed in the original LHC arguments. And so the two matter objects are directly interacting with each other. Again, you'd have something like this in something like a Feynman-Wheeler absorber-like theory if you didn't believe in GR. And interestingly, this was also discussed at the Chapel Hill conference. Okay, so Feynman talks about how, yes, there's a delay in this experiment, which we saw in the previous slides, but this could be due to the gravitational field, or it could be due to an action at a distance theory of gravity. But then he goes on to argue that if we did have an action at a distance theory of gravity, then actually whether we have a quantum or classical theory of gravity becomes perhaps a matter of definition. Okay, so if we go back to his experiment, then here's our supposition of the mass again. Well, now we can't have a supposition of gravitational fields, but in these sort of theories, we'd still have a quantum supposition of gravitational forces, of relativistic gravitational forces, and you could argue that something like that should not be possible in a classical theory of gravity. And indeed, it wouldn't show up in something like semi-classical Einstein gravity. Okay, so you could then argue that seeing entanglement can still provide evidence of a quantum theory of gravity, even in this case. But that perhaps depends on your definition of gravity, as Feynman argued. And actually, that was just one example of the many different questions on the applicability of LOCC that are appearing in the literature and appearing all the time. So, for example, gravity being a non-local quantum field theory with explicit non-locality in the Hamiltonian, or how it's difficult to define subsystems in gravity, and many more appearing all the time. So actually, then it'd be great if we could avoid this whole debate by coming up with a signature of quantum gravity that can be that does not rely on this LOCC principle. Okay, so that was a bit of a motivation behind looking beyond entanglement that we did a few years ago. Okay, so here, rather than using a general principle like gravity, classical gravity is LOCC, instead we looked at the weak field regime of gravity that's applicable to these tests, and considered what sort of differences we might anticipate for a quantum and classical theory of gravity. Okay, so here we go and split the metric into a background and a perturbation again, so you have this interaction Hamiltonian between matter and gravity. And in quantum gravity, you would quantize the perturbation, whereas in classical gravity, you might expect that you don't quantize this perturbation. So then if we assume that matter obeys quantum field theory, at least within the regime of the experiments, and we assume that we are working in a regime where we can neglect all of the interactions, then the stress energy tensor of matter is quadratic in the fields. And so if we plug that back into our Hamiltonian, then we find that in quantum gravity, the Hamiltonian is trilinear in quantum operators, while it's quadratic in classical gravity if we assume a simple Hamiltonian formalism of classical gravity, because we don't quantize the perturbation. Okay, so it's well known if you have a quadratic Hamiltonian, okay, this will preserve Gaussianity. Okay, so Gaussian state, or pure Gaussian state, is one fully defined by its first and second moments, or when its Wigner function is Gaussian for a bosonic system. Whereas a non-quadratic Hamiltonian can induce non-Gaussianity. Okay, so for example, this simple Hamiltonian with A for matter and G for gravity, that would induce a non-Gaussianity in matter. Okay, so then seeing non-Gaussianity in a gravitationally interacting matter could provide some evidence of a quantum theory of gravity. We applied this to a relatively simple experiment where you just have a single BEC self-interacting through gravity, and found that if you start it off in a squeezed Gaussian state, then this will go non-Gaussian after a short period of time if gravity is quantum. And some of the steps towards this have been undertaken in Lucia Hackemuth's group in Nottingham. Okay, so some advantage of this method is that we could just use a single system with a single quantum state. Again, you can just use local measurements. And now you could also rule out certain non-local theories of classical gravity, such as those based on where the Hamiltonian has explicit non-locality. Okay, because these, although they're non-local, so they create entanglement, they're still quadratic, so they preserve Gaussianity. Disadvantage, though, because it's not based on some underlying principle, perhaps, is that it's probably not going to be so general as entanglement in other cases. So, for example, we know it works in semi-classical Einstein gravity, and that would Gubitosi Penrose collapse, but we still need to see if it works in something like Oppenheim's or Tilley-Gubitosi models, whereas we know that they'll work for entanglement as long as you can make these theories local, because there have been some works on that recently. Okay, so that's 3 examples of how you could test for quantum gravity. Okay, LOCC inequalities, quantum non-Gaussianity, and entanglement. And what these seem to be telling us is that we need to look for quantum information properties in matter to evidence quantum gravity. But of course, that's always going to be challenging for macroscopic systems. And so it'd be great then instead if we could look for classical-like quantities that could evidence quantum gravity. But that doesn't seem perhaps very plausible because we're trying to evidence the quantumness of some system. And so then it makes sense that we need to look for quantum information properties. Or maybe it doesn't, because a few months ago we showed that if you just took a single BEC, let itself interact through gravity, then you could evidence quantum gravity by just looking at the heat capacity of the BEC. Okay, so the idea is similar to Feynman's again, that the natural state of a BEC is in fact a quantum superposition of particles in and out of the condensate. So according to Feynman, this leads to a quantum superposition of gravitational potential energies, whereas in classical gravity, you can't have that. And so that leads to a very different modification of the energy spectrum of the BEC. Again, in fact, for semi-classical Einstein gravity, this doesn't affect the heat capacity at all because it all averages out. And so you have a clear signature between quantum and classical gravity, whether the heat capacity is changed or not. Okay, so that's a relatively simple measurement to perform experimentally. But a disadvantage is that we need to really push the size of BECs to make this effect measurable. Okay, so we need to really increase the number of atoms. And there are some ideas on how to increase the number of atoms in the literature, but probably would have to go beyond even those. Though it has the advantage that we wouldn't have to squeeze. Okay, so that's now 3 different ways to look at quantum gravity beyond entanglement. But actually, that's just a small snapshot of all the ideas out there, and there's more appearing all the time. Okay, so there's a fantastic idea on looking at the measurement postulates of quantum gravity that Debashi spoke about yesterday. Related to that, looking at Legge-Gardner inequalities, looking at quantum coherence, non-commutativity, Fisher information, etc. Okay, so, and in all of these cases, just as what we looked at, there always seem to be cases where you can find advantages over gravitation-induced entanglement, and I really recommend going for these papers to understand what these advantages are. But also, of course, they also come with disadvantages, so it's probably about striking the right balance between the pros and cons for a particular experiment. Okay, so I'm going to skip over this slide because I think I'm out of time, and just summarize by saying that, in summary, with the advent of quantum technology, we're now getting closer to realizing Feynman's original dream of observing the quantum nature of gravity in the lab. However, challenges remain substantial, which has led to these alternative methods to entanglement. And arguably, there's not one method that's much closer to realization than another, or clearly better. But that's kind of, I guess, the motivation for future work in this field, that we'll find a method that can bring us much closer to experiments and test quantum gravity in a robust way as possible. So I focus mostly on theoretical developments in this talk because I think that's what I was asked to do. But of course, there's lots going on experimentally as well, like creating mechanical qubits and calling microsolids to the ground states. So while challenges do remain substantial, I do think with continuing theoretical and experimental advances, we are edging closer and closer to this judgment day of finding out whether gravity is actually quantum or classical, or perhaps more than that, seeing the effects of quantum gravity for the first time. Okay, all right, thanks very much for your attention.
We have another microphone for the questions. Okay, so we have time for, thank you very much, Richard, for this very nice overview of the activities and proposals in this context. We have some time for a few questions. Yes, so he should use Ivan.
Hi, thank you for the very informative talk. So some people have argued that one should differentiate between radiative degrees of freedom of gravity and non-radiative degrees of freedom, like Coulombic degrees of freedom. People have argued that they are fundamentally different, and some believe that what actual gravitational degrees of freedom are radiative, not Coulombic, and proving the quantumness of one set doesn't tell us anything about the quantumness of the other. And in your exposition, you haven't differentiated between them. Could you further elaborate on this point?
Yeah. So it's true. So that's been considered a lot. Like there's been lots of arguments on whether, maybe just radiative degrees of freedom are the real ones. But I mean, I guess I can only give my point of view, which is that personally, I think you can't make that distinction. I don't think it's physical to try and distinguish between Coulomb and radiative degrees of freedom. But, I guess you could say that the experiment as it is could not, if you believe there was a distinction, then it could not actually distinguish this, because, I mean, as I showed with this absorber-like theories, you can always think in a way, you can entirely get rid of like a graviton and to explain the entanglement effect. It could just be, a non-local interaction. But, I think really if we were to see entanglements, I don't think many people would really believe that, gravity is actually like some sort of Feynman-Wheeler absorber theory. I mean, we haven't thought that for the last 40 years, so why should we think that now? So I think, if we did see entanglement, then this would really tell us that, we must have something like the graviton, although maybe not directly testing that. It implies that, which is some papers by Bob Wold and his students. That's some very nice work on that. So that's what I say.
Thank you. So, any other questions? Yes.
So you mentioned that in order for the masses to get entangled, you need them to have enough time to communicate with each other, basically, right? But in the way you're treating the linearized gravitational field, this is a massless spin-2 field. Like, it's just a standard massless spin-2 quantum field. Then in that case, I'm assuming that you assume it to start in the vacuum state, which means that there is entanglement that could potentially be extracted even between space-like separated regions, right? So it's just, of course, this is way outside of the regimes of the experiment, but that specific paper that you mentioned there, they use a semi-classical approximation to reach their results, which only depend on the retarded propagation of information. That's why they see this. But in principle, there would be correlations that would be acquired due to the quantum degrees of freedom of the vacuum itself of the field.
So would you say that those are instantaneous?
I'm sorry, could you repeat that?
Will they be instantaneous, this entanglement? Or you're saying it's already there?
Not, I mean, yes, it would be instantaneous in the sense that like the entanglement's already there. So it's like it's analogous to entanglement harvesting, and the more mundane analogy is like picture a spin chain, where the ground state of the whole spin chain is of course an entangled state between each side. So if you just couple it to each side, you can extract a part of this entanglement.
Sure. No, I'm sure that's correct. I don't think that presumably wouldn't be the same entanglement though that you would see in this experiment, right? So it would be a different entanglement.
But I would argue that it would be even more evidence of quantum degrees of freedom of the gravitational field, because you'd be extracting entanglement that was already there. Right?
Yeah. But do you think it would be a much smaller effect, or is this an open question?
It would be a very small effect. I mean, we haven't even seen it experimentally with the electromagnetic field yet, so yeah.
Okay.
We have 5 minutes for a very urgent and short question, Daniel.
Thanks. Models like the Oppenheimer and other hybrids, the only viable ones, they do have decoherence and diffusion, and some of this was estimated, including their trade-off. They also, in principle, do not satisfy conservation of the angular momentum. Do you expect that it will be possible to have coherence of your system and isolate it well enough to be able, instead of looking for entanglement or explicit signatures of quantum gravity, more focus on exclusion of the alternatives?
Yes. This is the slide I skipped over, actually. So, yeah, I mean, I just focused on looking at experiments where you're looking for effects that you'd associate with quantum gravity. But you could do the opposite, and you could look for effects that you might associate with classical theories of gravity. So yeah, for something like DOC Penrose, yeah, I think that you could, well, in theory, hopefully, there's nothing telling us that we shouldn't be able to isolate the systems well enough such that then you could test directly for something like DOC Penrose, test for wave function collapse. And potentially that could be easier than these entanglement tests because now you just need one system, put it in a superposition, and then you look to see if it's decohered. So yeah, that's an alternative approach. A disadvantage of this sort of approach is that now, in a way, it's difficult to rule out theories entirely in this way. With the DOC Penrose, okay, maybe they might argue there's not a proper free parameter, but there always is a free parameter, like in terms of the spread of the how you collapse the wave function. And so you're probably only going to put constraints on this. Yeah.
So let's take the speaker again.
Your PC or mine?
Yes, before the next speaker. Yes.
I'm very happy to introduce Professor Giuseppe Marino, the director of the mathematics department, Renato Pezzopoli, which is one of the two departments who has organized with the nice conference.
Yes, it's my tag was there.
Good morning.
Oh.
Dear all, it's a great pleasure for me to bring greetings on behalf of the Department of Mathematics and Applications at University of Naples Federico II. I warmly welcome you to Naples for the 15th Annual Conference on Relativistic Quantum Information. The aim of the conference is to bring together experts from various fields connected to relativistic quantum information. We look forward to an inspiring exchange of ideas, new collaborations, and a deeper understanding of this exciting area of research. I'm sure these days will be rich in excellent talks and stimulating discussions. I also hope you will have time to enjoy both the scientific program and the beauty of our city during your stay. Finally, thank you all for being here, and a special thanks to the organizers for their efforts in making this event possible. Have a nice day and have a nice conference.
Thank you very much, Giuseppe. So I just want to say that there are still 3 seats, so I encourage everybody to take a seat. If we have no more, and I recommend people when they sit to start from the seats in the middle of the rows so that other people can come more easily. And if they are not sufficient, we have another room which can be put in connection with this one so that everybody can attend.
That's for the speaker.
Non trovo l'HDMI. Non trovo l'HDMI. Non trovi?
Okay. So wait a second. The two are the same? These two are the same? This is for the streaming. Maybe here. Shall I help you?
Please.
Very good. So while we are setting things up. The next speaker in this morning session is Jorma Louko from University of Nottingham, and he's going to tell us about waiting around for Unruh, so presumably how to detect analog versions of the Unruh effect. So Jorma, the floor is yours.
Thank you very much. 5, 6, is the microphone on? Okay, let me just check the visuals here. Okay.
Sometimes he goes back, but just try to go up or down again.
Okay, up and down works. Thank you. Thank you very much. Yes, thanks to the organizers for the invitation to speak at this very pleasant and very warm-hearted event. I'd like to talk about work done by the people listed here. So Diego was a PhD student at the University of York. Leo Parry is a current PhD student at the University of Nottingham, and Leo is at this meeting and will be speaking later in the week. Then there's Chris Fuster, University of York. Chris gave a talk yesterday. So this is a 4-person collaboration, and we think a paper should be out more or less any day now. The title may need some explaining. There is a keyword that we all recognize, the keyword Unruh. This has to do with the Unruh effect, that is the prediction in relativistic quantum field theory that an accelerated observer, accelerated local quantum system sees things different from an inertial quantum system. That is the Unruh effect. Then there's this keyword weighting, and that gives a hint that the role of time is, that time plays a role here. How long you do your observations, it has an effect. Sometimes you may need to wait for a long time to see anything. Sometimes you can adjust the period by which you do observation to extract something that you might not otherwise be able to extract, and that is rather the angle in which I'll be approaching the topic today. And then there is this word around in the middle, and that is a subtle hint that we are not talking about the standard textbook Unruh effect, which has to do with linear acceleration. We are talking about circular acceleration today, and the motivation for that is circular acceleration has more prospects for experimental realization. The plan, so I'll first recall a few basic things about the Unruh effect in relativistic quantum field theory and in its simulation in analog space-time quantum system, condensed matter systems. And I'll particularly think about why circular motion here is a better bet than linear acceleration. So it has some advantages, but it also has some puzzles. In particular, I've highlighted here low energy regime that has some peculiarities, and it's that low energy regime that I'll be addressing today. Then there's the technical bit, quantum dot, so Unruh the Witt detector if you wish. And there I'll give a brief review of the technical background by which I'll be approaching this thing. And the key concept there is you want to deal with a stationary system. What sort of notion of time duration observations are available when you have a stationary system? And then we'll get to the real business. So circular motion in 2+1 dimensions, the systems that you hope to be able to realize in a laboratory. And the key output here is highlighted in red. You have the option to fiddle with the sign of the interaction strength. Interaction strength does not necessarily need to be a uniform sign throughout all your experiment. You can adjust that sign in tabletop systems, and that will in fact help us in this 2+1 setting. So that's the plan of the talk. Now I appreciate that the format by which we are doing the recording, the format does not encourage questions during the talk, so I will go on, but please flag down any questions for the end of the talk. Okay. Unruh effect, prediction from the mid-1970s in relativistic quantum field theory that says an accelerated local quantum system, accelerated quantum observer if you like, they see different things than an inertial observer. And the showcase example occurs in Minkowski space-time quantum field theory. When you prepare your quantum field in the standard Minkowski vacuum, for inertial observers, this is a no-particle state. For a uniformly linearly accelerated observer, they see something non-trivial. They see excitations, they see de-excitations of their local equipment in a way characterized by a temperature-like quantity for which I have the formula there, A acceleration over 2 pi. And this is a genuine prediction for things that you can observe. My favorite picture is that I am sitting in my spaceship. I am accelerating, I am using my engines, and there on the ship I have a set of jars with different types of atoms, like this antimony, arsenic, aluminum, selenium, and so on. And once in a while, I open those jars and I look into them, and I see what fraction of those atoms are in their ground state, what fraction of those atoms are in their excited state. And I will see that this differs from jar to jar in a way that depends on the acceleration of my spaceship. So I see from those excitation and de-excitation probabilities in the jars that I am accelerating, and the prediction is that difference from jar to jar is characterized by the temperature formula, the Unruh temperature A over 2 pi. It's a real prediction, something you can observe. There are some idealizations that go into that formula, weak coupling, long time, negligible switching effects, and so on. But the key thing is this thermality aspect. It is something you can measure by looking in those jars. This effect is so real that you can cook your steak with it, given sufficient acceleration. To date, no steaks have been cooked with this effect. So I've given the formula here in a way where I've set c equals speed of light equal to 1. I've set h bar equal to 1. I've set Boltzmann's constant equal to 1. If you include those constants there, this is a quantum effect. H bar appears upstairs. This, in the standard setting, is a relativistic space-time effect. So there is a c in the formula, c appears downstairs. H bar in normal units is a small number, c is a large number. That coefficient there, it is a small number. The numbers say to get 1 Kelvin, you would need about 10 to 20 meters per second square. So no observation at present in this relativistic space-time setting. There is work, I should say, about indirect ways related to this effect, even in some classical observations related to this effect. But in this standard setting, there's no direct observation. So this is linear acceleration, and this is in the relativistic space-time in which we live. There is work on different types of acceleration. There is a similar effect that happens for all other types of accelerated motions you can have in Minkowski space. And for circular motion, the ideas to use circular motion, they go quite far back to the 80s. One selling point of circular acceleration is that in circular motion, you can stay in a finite-sized lab for, in principle, an arbitrarily long time. For linear acceleration, you can't do that, okay? So that's an obvious experimental selling point. There has been some work going back to the 80s with Bell and Leinos using a spin depolarization in acceleration, in particle accelerations related to this. That would be a topic of a talk of its own. There are some issues there. The basic issue to use that for this effect is that you don't have enough independently adjustable parameters. You'd like to measure a curve, but with that spin depolarization, you can't measure a curve. You can just get one point on that curve, and that doesn't leave much space for fitting, okay? Now, in analog space-time systems, Bose-Einstein condensates, possibly helium third sound surface waves, there is recent work where this circular motion could be realized over there, and I've mentioned some recent references there. There is, in fact, some experimental effort going in direction and is being built in Nottingham. Let me put up an overhead of what the benefits, what the challenges in this analog space-time setting are. So why now? So analog space-time, that is really my motivation today. Here is a cartoon of an experiment that is in planning, and parts of it have already been built in Nottingham. So you use a condensed matter system in which excitations obey a relativistic field equation. It's not a really genuine relativistic system, but it is a system where you have a Klein-Gordon type system. And one selling point is that the role of C in your analog system, it's no longer the speed of light in vacuum, it is the speed of sound in your condensed matter system, and that can be meters per second. Okay, so that brings the prospects down. Then you can build a finite size system like this, okay? And if you use circular acceleration in a finite size system, then you can run this experiment in principle for an arbitrarily long time. And finally, the selling point is, for those of us who have gone through the linear acceleration Unruh effect, the theory of it, we know that the relativistic time dilation has an essential part in the theory behind it. In a condensed matter system, you do not have relativistic time dilation available. You would somehow need to build it into the experiment. The selling point of circular acceleration in this context is that you do not need to ask your engineer to put a time-dependent redshift or Doppler shift factor in your experiment. You can do it all at the data analysis stage, because in circular motion there is a gamma factor, but that gamma factor stays constant in time. It's a stationary system. Okay, and I've got here a cartoon of how it might work. So what I have here, this is the Bose-Einstein condensate realization. The version that is being built in Nottingham is with helium surface waves, so it slightly differs. But in this cartoon, I've got a Bose-Einstein condensate here. So it's a plane-like Bose-Einstein condensate. It's like a pancake, or a dinner plate, if you like. Okay? And then what you do is you take a laser beam, you shine it at your pancake, and you make it go on a circular trajectory at the intersection point of your laser beam and your pancake. Now, I can't demonstrate this here very well, but the idea is you have your pancake here, you shine your laser on it, and you do this. And that's depicted in this picture there. The laser goes through the condensate. You collect the laser, and the laser has sampled some of the fluctuations from the condensate along this circular trajectory. And then you collect your laser beam, you do data analysis, and you infer what were those fluctuations. What do you see if you are on an accelerated trajectory like this? And the details of that would require a talk of its own right, but this is the basic experimental setup. This is where you use a 2+1 dimensional system. This is where you use circular acceleration. Looks good so far, doesn't it? What's the catch? Remember, circular acceleration isn't quite the same thing as linear acceleration. We had this nice linear acceleration formula. Can we rely on that linear acceleration formula in the circular acceleration case? I'll put up a graph that says mostly yes, but not always. So here's a graph. What is being plotted? So on the vertical axis, we've got this ratio of the circular acceleration temperature. And I'll say more about what the temperature means in an observational sense. The circular acceleration temperature divided by the linear acceleration prediction. So that's on the vertical axis. If circular acceleration was like linear acceleration, we should be getting a flat plane at 1. We don't. Things are different. Things depend both on the orbital velocity, measured in units of c. C could be the speed of light in vacuum. C could be the speed of sound in the analog system you're looking at. So things do depend on the orbital velocity, and things also depend on the energy on which you probe things, and that's what I've got in the other axis over here, measured in the units relevant for the system. So it's not a flat plane. Now you can observe that over most of your parameter space, it's not too far from unity. In particular, if you go to large energies, the thing flattens out, and it's of the same order of magnitude, so it looks pretty good. However, if you look at low energies, low detector, small gaps of the detector, if you think in that language, there is this low gap regime, small energy gap regime, where you go to 0. So if your experiment works at energies that are much less than the acceleration energy, then the prediction is the temperature you should be seeing, it's low. It's much lower than the linear motion prediction. Low temperatures would be more difficult to see in your data. So if an experimenter comes to us and says, my experiment, it really is well suited for this regime, what should I be seeing there? Then looking at this picture, we'd need to tell them, you won't be doing much, there's no point to do that experiment at all. Now, to date, no experimenter has come to us and told us definitely that they have a system that is adapted to this low gap regime. Okay. But the spirit for today is we want to be prepared. We have a control of what's happening over here, and there is an order of magnitude given by the linear thing. If an experimenter says, my system is well adapted to probing this regime, what do they do? As a theorist, we'd like to tell them, how can you extract data from your experiment? So that is what I want to address today. How do you get something out of this small gap regime? And the tool is, now think of time. It will necessarily be take finite time to do your experiment in the lab. This picture says you've done it for an infinite amount of time. What room do you have if you do it for a finite amount of time? Can you enhance the effect over what you see in that picture? Why do we think this should be possible in the first place? I mean, infinite time, finite time, something goes to zero. Why do we think that a finite time would help you at all? There is, in fact, a precedent that goes back to a talk that I gave at the 2016 Relativistic Quantum Information North meeting. And there is a precedent that has to do with the linear acceleration, and there we are looking at large gap limit. There is a similar balancing act there that has to do with large gap. So the basic problem in that setting is if you do your experiment for a finite amount of time, then at large gap you don't see thermality. You necessarily need to go to large enough times. And we showed that given some way of how you turn your system on and off, you can address the large gap, large energy regime in polynomially growing interaction time, given some fine print. The graph here is how you turn your system on and off. You keep stretching the time by which you turn and off. And the outcome is you can do it in a polynomially long interaction time. You don't need to do exponentially long interaction time. You don't need to wait for longer than the edge of the universe. But that also taught us there is some fine print in the system. If you do it in a different way of implementing the long time limit, then it's not quite polynomial anymore. So there is some subtlety when you start playing with this time. So there is hope. Playing with the time is something we want to try, but we can also expect that there will be some challenges. And I'd like to address now that. So I've got here three overheads on the basic mathematics of the technical tool, the quantum dot, the unroot-Witt detector. I'll just flash over these three overheads. Many of us are well familiar with the theory that goes here, so I'll just focus on the bottom lines. On the third overhead, we'll get to the things that are really relevant. So I will do it in the relativistic setting. We've got a quantum field, can be a scalar field for me, will be a scalar field for me. I've got a two-state detector, spatially point-like moving through the space-time. Field originally prepared in the Minkowski vacuum. And then there is the interaction term. The interaction is modeled on the dipole interaction by which the electromagnetic field couples to atomic orbitals. It's a good thing to do. And that interaction knows about how you switch your system on and off. And then you do your mathematics. You prepare the system in Minkowski vacuum, and one state of your two-state detector, you do time-dependent perturbation theory, and you will get a formula for the excitation probability of your system for E positive, the excitation probability if E is negative. And there's that formula. And so this is a very general theory. For us, we have a stationary system. So this is where the real fun for us begins. So for the stationary system, this Weitman function, the two-point correlator of the field, it's time translation invariant. You had a double Fourier transform there. Things depend now on the single Fourier transform. That's what you can play with. Effective temperature, right? So if you had a real Planckian, if you had a real thermal bath, you would expect de-excitation and excitation probabilities to fit an exponential law. We use a notion on effective temperature that fits to that exponential law, and we use this notion of a temperature. Long interaction duration, that's where we are heading. Okay. Now here I'm really skipping the detail, but the point is, if you want to go to this long interaction duration, your mental picture is long time at approximately constant, then some switch on and switch off periods at the end. Then I assert that in that formula up there, you have this mod chi hat squared. It divided by the total time, it goes to a delta function, and you get this W hat over here. This is the graph that I showed you earlier on. So to consider finite time, we need to think of delta tau not quite as infinite as here, but finite, and we need to think of the approach to infinity. And when you look at this formula, you'll see where the problem is. So we have this green expression here approaching delta function. 2 plus 1 massless fields is what we are interested in. That W hat, it turns out to be discontinuous. The problem is in 2 plus 1 massless fields, there's an intrinsic 2 plus 1 effect that tells you something funny is happening at small gap. And here it tells you you are trying to multiply a discontinuous function with a delta function. When you go to a small gap limit, that just doesn't work. And that is the subtlety that approaches here, that we need to address here. Now, I understand the time is limited, so let me tell you the bad news first and the good news then. The bad news is the naive attempt to do this doesn't work. We took what we did before, and now we try to look at the double limit, small e, long time, and we try to extract the finite temperature out of it. No, it doesn't work, okay? You still have a positive power law over there. It just doesn't work with these pictures. And when this comes out, you think that that's it, and there's basically no paper. But the failure here, it's actually quite instructive because it tells you exactly what it is you need to fix. And what you need to fix is, in these pictures, you are always working with one sign of the interaction. It's always positive. The calculation tells us we need to relax that to enhance the effect. And here I'm looking at the outcome. Okay, so I think I'm basically down to my last few minutes. So how much can I possibly tell about this? I was hoping to give this talk in the other room where there was a blackboard available where to put some pictures to these formulas, but that is now not going to work. I'll just have to assert that what we need for the long time limit is this. What we need for the temperature to be finite in the double limit is this. And I need to assert that if you think about delta functions and how you approach them with bumps, there's a contrast over here. The top line tells you you have some sort of a bump. And the bottom line there tells you if you integrate over something near the center of the bump, you should be getting less than the width of what you integrate over. And with a bump that goes to infinite height, that just doesn't work. So that's the reason why in those pictures I showed on the previous overhead things did not work. But it also tells us how to fix things. Remember, here's something that has a bump. It goes to a delta function. We can go and adjust that bump to be a double bump. 2 humps with something 0 in between. There's nothing wrong with that. But it just tells you that you need to make this switching change sign someplace. You need to turn the knob so that somewhere you have a positive coupling strength, somewhere you have a negative coupling strength. We give examples of this in the paper. And the outcome, you are afraid that the details of how you do this turning up and turning down will affect things. They don't. And here I've got some pictorial and formula evidence saying you really manage to extract the effect by doing this. And no significant fine-tuning is involved. And that is the bottom line. And yes, okay. So 2 + 1 is experimentally implementable. Part of the experiment is already in construction. For the data extraction, you need to worry about peculiarities of 2 + 1 things. And the way to do it in the small gap regime is by adjusting the strength of your coupling in a suitable way. I'll finish here. Thank you very much.
Thank you very much, Jorma. As usual, great talk. I have a question, I guess, from the, and we've discussed this a little bit from the devil's advocate perspective. I do like a lot this, by the way, let me tell you, but let me just tell you. So here, and you give me a criterion, so I want to discuss this criterion. So the reason why the two temperatures are not the same, right, is because you are working with a state that's not KMS with respect to the tangent vector to the trajectory, right? So there's no real thermality in that sense. So when you have a qubit, which is a two-level system, right, you can call the state thermal no matter what it does. There's always a temperature that you can associate with it. I can engineer it so that I have a temperature. So my question would be, so of course, one can, instead of doing the circular under effect, one can do arbitrary trajectory under effect, like some kink, for example, some easier experiment, like bouncing some atom against a wall, which is a ton of acceleration, right? And I wonder, right, because in that case you get a temperature, I would say it's a very bad one in terms of how it would relate to the Andrew temperature, but it is a temperature in the sense, effective temperature in the sense that you ask. So where do you draw the line of what you would call the Andrew effect and what you would not, according to this? Is it having that ratio that you mentioned close to 1? Because I'm certainly can engineer it so that I'm in a regime that... Anyway, that's just, I want to hear your opinion.
Yes, there is room for personal opinion on where you put that line. So here, the situation is stationary, okay? If you put in some arbitrary trajectory, then you would not expect to have stationarity. Here you have stationarity, and and we've relied on that stationarity as an essential part in doing the analysis. I'm quite comfortable personally thinking of these stationary situations as versions of the Unruh effect. If you have something that's non-stationary, then you may need to twist my arm a little bit more.
Can everyone hear me fine this time? Okay, great. So I was wondering, like, this reminds me a bit of the discussions in high energy physics of like linear accelerators versus circular accelerators. And from the equations, it didn't become too clear to me whether there would be an issue of Bremsstrahlung. So the accelerations that you have here are like two different accelerations combined. One of them just to sustain and the other one to actually increase the velocity. So I was wondering, how is Bremsstrahlung reflected in the calculations? Like, it didn't become too clear to me.
Yep, very good. So here we are saying we do not observe what is being emitted into the field as an outcome of the interaction. We are just saying, what does this accelerated thing experience in terms of transitions up and down, if we think of it as a real quantum dot, or in the laser experiment, what is the information that the laser extracts from those fluctuations? So here, I've never asked, what is the back action on the field, what is the Bremsstrahlung, if you wish. There clearly is such a thing, and you need to worry about it. And a version of that will be worried about by Leo Perry in a talk later in this meeting. So to put it in other ways, we just assume that there is some friendly neighborhood external agent who does the accelerating. We don't ask what is being emitted in the field as the outcome of that.
Jorma, again, thank you for a very informative and nice talk. I have some surprisingly practical question. As a theorist, 2 + 1, 1 + 1, n + 1 is fine, but you're specifically talking about the simulations. So how we actually, you actually using Weidmann functions which are appropriate for 2 + 1. So there should be some way that forces the motion and the entire process to be really like 2 + 1. How do you do it, or how you, theoretically at least?
I should refer to work that Nottingham students, including Leo Perry, are pursuing on this matter. I don't think you are talking about it here, but so this is a question that you can approach by taking a, say, circle in one dimension in 3 + 1, then thinking what happens when that circle is small in size or large in size. What happens to these acceleration effects in that limit? So it is a question that needs to be asked, and it is under investigation. In the experimental setting, you cannot put the fourth space-time dimension on to have some potential that confines your BEC on a plane. Or if you are working with those helium surface waves, well, then there's solid-state physics that puts them on the surface. And you need to worry about those surface effects, okay? And
Ready? Namely, that it seemed to me that there was a slight difference in the ideal situation with a circular motion. You would have a quantum two-level system coupled to your field. Here instead what you do is that you are just measuring, so I think that in effect, as you showed, the relevant thing is the coupling to this Weidmann function, and what your experiment is doing is really measuring this Weidmann function along that core line, right? Yes. So if you want to comment?
Yes, fully agreed. Right. So we are thinking of this two-state system that is being physically accelerated. That's the prototype. But then when in this version of the experiment that I was thinking, there's this interaction point going around, so there's no material thing going around there, but that laser beam is collecting, it's sampling the Weidmann function, if you like, and then you can go and do a data analysis and say, you've got this and this spectral density. This spectral density is the W hat that I had over there. And so it is a measurement of the same effect in that sense. And I'm sure that within this crowd we could have various opinions on how good the analogy these things are, but let's not do that on my time.
Sure, we have time for coffee. So let's take the speaker again. I can give you 1 minute or 5 minutes, and then you will have 10 minutes. If you need a bit more time, you take it from the question. Yes, okay, yes. So, exactly, they were mentioning that you don't, otherwise you can use the other side, I guess.
I mean, the other side is the same thing.
Okay, I see. So, if you cross the line, you don't appear on the video recording.
Okay. I see. So I should try to stay here.
Like we're not okay. No.
And how is this? This should go in a presentation mode.
While you just get this ready, the next speaker is. Sorry, I should use.
Can you put this in presentation mode, please?
Yeah. Sorry.
The next speaker is Schützhold from the Technical University of Dresden, and he's going to tell us about the stimulated emission or absorption of gravitons by light.
Oh, okay.
So, Ralph, the floor is yours.
Okay. Okay, does microphone work? All right. So then, welcome everybody, and let me also join the other speakers by thanking the organizers for putting up this very, very nice meeting over here. And in my talk, I will talk about some ideas about the emission of gravitons by light, and to give you some sort of motivation. Now, try. Okay, let's revisit some very interesting experiment, which is Franklin's kite experiment. Here you see a nice painting. It's probably not too realistic, but it already conveys the main idea. So what Franklin did is to fly a kite wait for a thunderstorm, and then fly a kite into the thundering clouds with the goal to collect static electricity, which then moves down the line of the kite. And then here he had a metal a metal key on it. And then he actually, that's at least the saying, approached his hand to the metal key to feel the little sparks, and that's why proving that sort of this lightning they were observing was basically the same phenomenon as the electricity they already had in these lab experiments with the Leyden jars and rubbing amber and leather and so on and so forth. And so this is at least how it's reported. But I would say, of course, this is an extremely dangerous experiment, so I would not recommend anybody to repeat it. And he was really, if it happens like this, he was lucky to survive. And there's our stories that other people did the same experiments and they were less lucky. So it's very dangerous, but I think it's very important. And one way why it's important is that it helped us to unify, to understand that the lightnings we observe in the sky or some thunderbolt coming down to Earth is basically the same electric phenomenon people already knew from the lab, from these Leyden jars and other things. And that helped us to unify the whole electricity and later on magnetism and everything. And I think even up to nowadays, we arrive at a standard model of particle physics, and this is one important step. But I would also say another important step this experiment marks is that we make the transition from passively observing some phenomenon, just as lightning, you just look at lightning and see, oh, there it is, and make the step to actively manipulating it with these kites and later on also with lightning rods. And I think that this also paved the way to nowadays power plants and so on, that you say now we can not just look at the phenomenon, but also manipulate it and do something with it. All right. So this was all an example from electromagnetism. But now let's come to another force of nature, which is gravity, and especially, let's look at gravitational waves. And also here a little bit about history. You all know that the gravitational waves have been predicted by Einstein more than 100 years ago. Here's one of these papers. And at that time, many people said, yeah, they are so weak, there's no hope of ever see anything like this. And yeah, it's not surprising, it took more than half a century before first indirect evidence was found with this very famous Hall's-Taylor binary pulsar. So here you have far away some heavy masses which are orbiting each other. And then according to this theory, they emit gravitational radiation and thereby lose energy. And this energy loss, when monitored over time, really fits very, very nicely with what you would have predicted from this Einstein's theory of gravitational wave emission. And that has been sort of the first indirect evidence that gravitational waves really existed, but from a very far away pulsar. And then, as you all know, almost 100 years later, after the theoretical prediction, gravitational waves now have been directly detected at LIGO here. You probably all have seen these pictures over there. And these two, the indirect and the direct detection, have both been awarded with the Nobel Prize. I mean, Einstein also got the Nobel Prize, but not for this one, but I think that was also a great achievement. So he would probably have deserved more than one Nobel Prize, but he just got one of them. Okay. So now we have these gravitational waves, but I would say at the moment, we are still at the stage where we passively observe this gravitational wave, and now the question is, can we make the step, or what would it take to make the step to actively manipulate them? Okay. Oh, sorry. Okay. So can we make the step for gravitational waves now from passive observation to active manipulation? Or one way to put this question would be, can we have something like the Hult-Taylor pulsar, but in a lab? Can we do this whole thing in the lab? And I would say, yeah, it's very easy. You just take, say, 1 kilogram mass here, 1 kilogram mass here on a rod, and then rotate them around. Then you solve the Einstein equations for this system, and you say, ah, look, there are gravitational waves emitted. Very easy. But things are not so easy, since now if you look at the power emitted by gravitational waves over here, that's the well-known quadrupole formula. It's sort of the analog. You all know the dipole radiation formula and electromagnetism. That's now the gravitational analog. It's quadrupoles here and the third time derivatives, but otherwise it looks very, very similar. And it's basically the same equation you can use for calculating the power or the energy emitted by these pulsars over here, which gives you the energy loss. So this is Newton's gravitational constant over speed of light to the 5th power. And here the quadrupole moments, third time derivatives, and everything squared. So it stays with the Newton's constant over speed of light to the 5th power, omega to the 6th power in frequency, 2nd power in mass, and 4th power in the typical characteristic length scale. Problem is, if you look at this prefactor, calculate this in SI units, you see with the C, Gn is small, C is large by the 5th power. This is a very, very small number. So 10 to minus 55 over here. And even if you compare this to h bar, which is 10 to minus 33, you see that you have something like 2 kilograms at 1 meter and then rotating with 1 hertz, you would emit far less than 1 graviton in such a way. And then of course you could say, yeah, if you emit less than 1 graviton, can you really say I have emitted a gravitational wave? Problem 1, and problem 2, there's no hope to ever measure this. So it's really, really tough. And that's why we have to do something else. But I should, so the goal would be to say we emit, the goal is to emit or absorb, but let's say emit at least 1 or ideally many gravitons that we can really say we have emitted some gravitational wave. And in a verifiable way, that means somehow you want to measure that, there is some energy which must have been emitted into gravitational radiation. And also, if you remember the first talk of today, I should make a disclaimer here. So here, this experiment I'm proposing or discussing is not, the idea is not to prove that really the energy of gravitational radiation is quantized in units of h bar. That's a totally different experiment to do this. So here we just assume it's like this. And then we say we want to emit lots of gravitons. So a tiny amount, which is less than a graviton, is not enough. Okay, since this is very hard, now we have to come up with some new ideas. So first idea is we go for stimulated emission of gravitons, which you also know from lasers. If you have some laser and there are lots of photons in one mode, then to emit another photon into this mode is much easier than sort of in vacuum. And you see here there's c to the 5, so speed of light plays a role, so things which move fast might help. So here the idea is to use light, something like an optical Weber bar, where here there are some pictures from Maryland universities where they had some reconstructions of the real Weber bars. If you don't know, Weber bar was just a cylinder, which you hopefully cool down to the ground state, and then gravitational wave comes, excites the cylinder, and then you measure that the gravitational wave has passed by. They claimed it had worked, but I think it was not quite a successful experiment, but it was, I think, very important for the traditions, but for the development of gravitational wave detection. So here would be basically the idea to do the same thing with light, but with light we don't start in the ground state, we start in a highly excited state, so we can also emit, not just absorb gravitational waves, but also emit them. I mean, in principle, you could do the same idea with a mechanical system like a rotating vibrating barbell, like here, but if you then plug in the numbers, it's still quite hard. So here, let's stay with light. Oh, sorry. Okay, so now the idea is to say we assume we have a gravitational wave, that we want to have stimulated emission, and we use light to emit another photon or more than 1 photons into it. So we have some gravitational wave here, and to make things precise, I take a gravitational wave propagating in z direction, which is given here, and I just use for simplicity plus polarization and the transverse traceless gauge over here, but this is just details here. The line element is given like this, so dt squared. then here 1 plus h dx squared. H is the time-dependent amplitude, or space-time-dependent amplitude of the gravitational wave. That's basically what the LIGO people measured over here. Then dy squared, you have 1 minus h, dz squared, nothing happens. And since h is so small, 10 to minus 22, I neglect terms of h squared and higher. Okay, so this is our metric with the gravitational wave passing by. And now in this metric, I consider my light. That means an electromagnetic field. And also to make things simple, I say it's polarized in z direction, which means it propagates in xy direction. So the light is propagating this plane, and the gravitational wave is orthogonal to it. And then you can just write down the effective Lagrangian for this electromagnetic field in this metric, and it looks like this. And there you see you have 1 minus h and 1 plus h in front of the two magnetic components. This is By, and that's Bx. And here the electric field doesn't get any modification. And then after quantizing the electromagnetic field and so on, this is the interaction Hamiltonian, where you have here the difference between the two magnetic field components squared and the gravitational wave amplitude out front. Okay, and with that, then it's quite easy to calculate the energy transfer. That means the energy change in the electromagnetic field due to the interaction with the gravitational field. And if you believe in energy conservation, that means that this must have been emitted or absorbed from the gravitational field. And then the energy transfer is given by this. So this is the expectation value of the energy of the electromagnetic field itself, time derivative. So it's h dot, time derivative of the gravitational field amplitude, and then here this expectation value of these two magnetic components squared. And that would be sort of an analog of this Hals-Taylor curve over here if you can have a lasting energy shift. And there you see, so in the first half period, where we say h, the gravitational wave amplitude is say increasing, so h dot is positive. That means photons propagating in x direction, these are these guys here, they lose energy, whereas photons propagating in y direction, they gain energy with the gravitational field. But then in the second half period, if the gravitational field goes down again, that would be just the opposite and vice versa, which means if you have a photon propagating and then the gravitational field goes up and down, netto, before and after, nothing happens. So the photons would not gain some energy unless you change these directions over here. And that's basically what we want to do. And then if you believe in total energy conservation, you would say energy loss of photons means emission of gravitons, energy gain of photons means the absorption of gravitons. But you then have to change the directions in a clever way to really make a lasting energy shift. Okay, and that's sort of first beam splitter, but we'll explain why this is later. So let's just assume the photon goes up. And the idea would be that right here, when the photon starts to go up, that's the place also where the gravitational wave starts to increase. Then the photon is here propagating back and forth, since you want to have everything here in a small space like LIGO, like say 1 kilometer or something. So the photon goes back and forth, so propagates in this direction. And all the time, since it's sort of all propagating in the same direction, if the gravitational wave increases, this photon gains energy until it's here. And here, say, this is the top place where the gravitational wave would not go down again. So if the photon would continue this way, it would then lose all the energy it gained. But now comes the clever point, oh, sorry, clever, but the point. Now the photon is reflected into this direction. And during this short reflection, the frequency is conserved. So if the frequency or the energy of the photon was increasing up to here, then it's reflected. Then gravitational wave goes down, but now it's propagating in the other direction. So energy gain is increasing even further. So over here, they then have really a lasting energy shift compared to the initial state. So here, if the photon does this trajectory, goes through this arm, the energy increases. And you can imagine then the other way, if the photon goes to the other arm, then here energy decreases, then it would increase again, but now it's again reflected and it decreases even further, which means then you have an energy shift or frequency shift between these two ends over here, and the idea is then to measure this. And then this means that if one photon with a given frequency enters here, would have a tiny higher frequency here, a bit smaller frequency there. And to measure this, then they are sent through a delay line over there. where then these small different frequencies would generate a small difference in phases of the two photons. And that's then measured over here with another beam splitter and via some interferometer. Okay, so basically this is here, this is the sort of like a half a Sagnac interferometer with the idea that the energies interact with the gravitational wave to change the energy. That's done. And then this one, then the gravitational wave is already passed by and is gone. There's a question, yeah? Later, okay, later on, yeah. I'll try to speed up that we have some time for questions at the end. Okay, yeah, so this is sort of the interaction with the gravitational wave, and this is happening afterwards, this delay line, that can be quite long, and then that's just to get a phase. So let's put in numbers. So the gravitational wave, I assume an amplitude of 10 to minus 22, frequency in the kilohertz range, and for the electromagnetic wave, just optical photons, 10 to 15 hertz. Then the frequency shift per photon is 10 to minus 7 hertz, so that's the difference over here. And then if you have a delay line with here, of course, that's not to scale, with 10 to the 4 reflections, that's possible with nowadays mirrors and cavities, then would be a length of 10 to the 4 kilometers or a delay time of 0.1 seconds, where this frequency shift then is translated into a phase shift per photon, 10 to minus 8. And to measure such a small phase shift, you need the many photons, which if you just do the Poisson limit, just standard classical photon states is 10 to the 16 photons. And then if you look at here, 10 to the 16 photons, and each of them hertz, that means you emit a lot of gravitons in this case, so it's much, much more than one. And if you plug in numbers, the average power you need in here is in the order of watt, so it's not totally crazy what you have here. Okay. Oh, sorry. Okay, now all this was classical if you want, but now we can say, okay, what can we do with quantum states of photons? Of course, we all know squeeze states can enhance the sensitivity. So as an extreme example, we can use these noon states, which are sort of from, if you look here, it looks like noon. And the idea is that sort of either all photons go this way and none here, or superposition, all photons go this way and none is here. That's a highly non-classical state. But if you would prepare this, it's very hard, but assume we can do this, prepare this state, then in one case you have energy gain, in the other one you have energy loss. And then you see, to make this measurable over here, that the state with or without gravitational waves are distinguishable. You just need something, a sign change, which means you get the Heisenberg limit, what is called the Heisenberg limit, where the phase accuracy scales with 1 over photon number instead of the Poisson limit, where the phase accuracy scales with 1 over square root of photon number. This applies to classical, ordinary classical laser fields, and that's only possible with these very highly squeezed non-classical states. So far, this is sort of quantum photon field, but classical gravitational field. But now let's do one step further. As we had in the first talk, can we address quantum aspects of gravity in such a case? So let's say here we have our photon state. Then here is the quantum state of the gravitational wave with some average energy. And then sending this through this line, then since here we gain energy, we lose the energy in the gravitational field. And in the other way, here it's the other way around, we gain, the gravitational wave has to gain energy, all assuming energy conservation is still valid for gravity. There are people which don't believe that, but let's assume this here. And then the question is this entanglement? And that's a bit similar to this entanglement of the two masses at different positions, where the Newton field is entangled, but here this is now the graviton field, the gravitational wave field, which is really a very different setup. And the question is, what's the overlap between these two states? And if we assume that the gravitational wave is in a coherent, highly excited coherent state, so it's basically classical, then this overlap, since this is a large number of gravitons, but much, much smaller than the one which were initially in there, this is near unity, which means you can basically factor this out and you have the ordinary thing back, you get the full visibility of your photon interference experiment over here. But now let's assume, just to take an extreme example, that your gravitational field is in a Fock state or thermal state, but let's take a Fock state. Then, since this is more than one graviton, many gravitons actually, This is basically 0. And then basically we have no interference over here. So with this way we could distinguish between coherent state and Fock states of the gravitational field now. And that would then be some example for gravitational decoherence, which also I know some people here were studying. Of course, this is a crazy example, and most people would believe it should be a coherent state. But history has told us, since just the fact that many people believe that doesn't mean it must be true. So it's always good to test. All right. So that brings me to my summary. If you want to look for details, here is the paper over there. So I was talking about gravitational waves and how to make the important transition between passive observation and active manipulation. So something like the Hals-Taylor pulsar in the binary. And here the idea was to make stimulated emission with using light with such a geometry over here. And I think a very important point is that here in the first half, you have the interaction time. Here the photon interacts with the gravitational wave. Whereas in the second part, you have just the phase accumulation time, and that can be already much, much longer, where the gravitational wave is already gone. So this is a sort of an important difference to LIGO, for example. We have to do everything within the gravitational wave, and that actually could also make some advantage, but of course, this is still very, very hard to realize. And as an outlook, if you then do this, and you can even insert non-classical photon states, you could test certain aspects of gravity, even though we don't test whether really the energy is quantized in units of h-bar, but you could distinguish between the coherent and the Fock state, for example. Okay, with that, I'm finished, so thank you very much for your attention. I hope this was.
We have time for questions. Uwe, you have a question? So wait for the microphone, please.
How do I?
Yeah, my question has two parts. First, what is the bandwidth of your detector? I mean, how much can you tune into different frequencies?
Okay. Yeah, here the point is that it now depends on whether you want to have resonance effects or whether you want to just see one cycle. Here the photon time, travel time, must match the gravitational wave period. If it's totally off, too long or too short, it wouldn't work.
But you don't know how much the bandwidth actually is. I mean,
no, I don't know. You can calculate. Depends on how. If you just want to say one cycle of the gravitational wave, then if you divide by 10 or 20%, doesn't matter. If you want to make many cycles, of course, it's then more.
Many gravitons means how many again?
Oh, a lot. I mean, you can.
10 to something.
Yeah. I mean, 10 to 16 photons with 10 to minus 7 hertz.
Okay.
That's 10 to the 9 hertz. So it's a million gravitons.
And the next question is, I mean, these non-classical states, of course, they're very unstable for large n.
Of course.
I mean, you can do maybe Schrödinger states, noon states of like 10 particles if you are very lucky.
Yeah, that's what. Yeah, of course, these noon states, they enhance sensitivity, but of course they are also sensitive to everything else. I mean, yeah, that's the nature. Yeah.
No, I mean, it's unrealistic. Let's put it like that.
I would say I'm really happy if they do this for classical light first, and then we can speak about. Yeah.
Any further questions?
Yeah, thanks, Rolf. Very interesting idea, but as is the case with all things gravity wave connected, sources of noise are pretty bad. Have you looked into that?
Not really, but I would say I think they should be roughly comparable to what people do in LIGO, since the setup is not so different from the orders of magnitude in LIGO. But for example, here you shouldn't have two totally separate delay lines. Probably it's clever to use the same mirrors, that both photons can go through the same delay line in case one of the mirrors makes a little jump, that it doesn't screw up the relative phase. But I would say it looks like it's very similar to LIGO, but yeah, I have not done a full sort of study.
Thanks.
Yeah.
Any further questions? Maybe while we wait to see if you have any further questions, I understand from your picture that still this could be implemented in a sort of on a plane, right? So that you can have your freely suspended mirrors.
Yeah, I mean, the light is going in the plane, and gravity wave is doing this. Yeah,
Exactly.
that's the same as in LIGO. Yeah.
So you have some additional propagation, but everything happens on a plane.
The idea is that all the photons are in a plane.
Exactly.
Yeah.
So that you can exploit
you want to have kilometers arm length, so it's probably clever to have this.
Exactly. Plus the freely suspended mirrors with isolation. So do we have any further questions? Otherwise, I would suggest that we will have the coffee break, but Gaetano might have a... So let's thank the speaker again and all the speakers of this first morning session.
Very short, while going out, please sign the cost present.
Yes, so remember to sign the forms for attendance.
There will be somebody of the agency.
So we will reconvene at 11:30 and
Nice. Thank you very much.
Very good. So the first speaker of the second part of this morning session is Daniel Carney from Lawrence Berkeley National Lab in the US. And he's also going to talk about testing quantum gravity, also giving some discussion of the interpretation, because besides actually trying to do these measurements, in some cases interpreting what are the conclusions one can extract from such measurements is also an important and sometimes subtle issue. So Daniel, the floor is yours.
Yeah, great. So do I have to hold that, or do I just talk into this? Yeah, no problem. No problem. Okay, yeah. Hello. Okay, good. Yeah, thanks very much for having me. And I want to thank the organizers particularly because I had some fiasco yesterday. So this was my life for the last 48 hours. Yeah, it's a 12-hour flight from San Francisco to Rome, and somewhere in the middle of the ocean, the pilot said something like, "Oh, the engine is broken," which is really relaxing. So I got to spend 24 hours in Keflavik, which is the thing next to Reykjavik. It's a little less scenic. That was my view. So anyway, thanks very much. I'm happy to be in Italy now. This talk is going to be sort of similar to Richard's talk in spirit. I'm going to talk about a sort of different set of ideas, and I'll give a few different opinions. But it was really nice that Richard set up a lot of what I'm going to say. So the question we're asking in this testing quantum gravity world is a very simple, conservative, experimentally minded question. It just, is the gravitational field a quantized degree of freedom? So that, I think, is in scare quotes because it's not precise. You want to make this precise, you need some operational meaning of that. So this sort of cartoon of an experiment is how I think about this. So the question you're really going to ask is, can I take the gravitational field and put it in a quantum superposition of, say, two distinct states? And then really the question is, can you measure this, and what do I learn if I do? So the cartoon, right, is how would I think about such an experiment? I would take some object. So an example object that people are seriously thinking about, this picture up top is a levitated bead. It's a silica bead. It's about a micron width. So it's some kind of meso to macroscopic object. That thing has a gravitational field, albeit a small one. What you'd like to do in principle is superpose it in, say, two locations or something more sophisticated. The general baseline assumption would be that if gravity is quantum mechanical in the same way that the electromagnetic field is, the gravitational field would come along for the ride. It's superposed similarly. How do you measure this? The same way you measure any gravitational field, you take some other object and let it fall. Okay, and that's the third cartoon. I have some test mass, some detector thing. I'm going to let it fall onto this superposed gravitational field and ask what happens. So I've been working on this for many years now, and I've evolved into a very curmudgeonly old guy about this. So my view personally is that this question, is gravity quantum, quote unquote, is ill-defined. It's not actually scientific per se. And if you really want to think about what you're doing here, you really have to go back to the scientific method and say, what is a test? You have to have two models, a null hypothesis and an alternative hypothesis, say what they mean in some experiment, and claim that your experiment distinguishes them. I don't mean to be pedantic, but this is how I'm going to frame the talk, by giving you some examples of such hypotheses. So I'm going to go through a list of types of experiments and what they look like. First, I'll talk about what I view as the null hypothesis in this field. Then I'll talk about some alternatives that people have proposed. And then I'll go through what they would mean for experiments in this order, thinking about single graviton detection, thinking about detecting entanglement via gravity, and then finally thinking about searches for anomalous noise in the gravitational interaction. So I put this slide up because I give this talk to many diverse audiences. Some people think this is obvious, and to some people this is totally alien. Okay, it's sometimes you'll hear things like, we don't know how to quantize gravity. That is not correct. Okay, we know how to quantize gravity in the regime that we're going to test it, which is I have a lab system at very low energy and an approximately flat background. In that setting, we have a theory of quantum gravity for the small gravitational fluctuations you're going to actually see. Here it is. There's an action. You can write it down. You can quantize it just like E and M. Famously, this is not renormalizable. For a long time, that was viewed as a fundamental problem, and in some ways it sort of is, but it's also now known that most field theories are not renormalizable. The standard model with neutrino mass is not renormalizable, and yet it makes very definite predictions that we go and observe. So what I want to emphasize is that this system also gives definite predictions that you can go and check. The problem starts when you have curvatures that are of order of the Planck scale, so like near a singularity. Then there's this infinite series of terms. We can't compute anything. It breaks down, blah, blah, blah. Okay, that's a real fundamental problem. But at low energies, R over M Planck squared is like 10 to the negative 100, and this Taylor series converges very quickly, and you can predict things. This model is just saying that gravitational fluctuations are quantized into gravitons, just like the electromagnetic field is quantized into photons. It's also sort of the only thing that you can have, assuming that there's unitary time evolution, Lorentz invariance, and sort of space-time locality, and that you want to reproduce the Einstein equations. So this list at the bottom comes from old papers by Steve Weinberg in the 60s, where he really showed that under these assumptions, this is all you can get. So in my view, what these experiments test actually are one of these hypotheses violated by gravity? So does gravity violate unitarity, or does gravity somehow break Lorentz invariance, or locality, or something like that? Okay, so that's the null hypothesis. What's an alternative hypothesis? An alternative hypothesis is where gravity violates one of those assumptions. So now I'm thinking about this in a sort of more tabletop two-mass system. Okay, so non-relativistic gravity to start. So on the left, if I have quantized gravity, psi1 and psi2 are the state of two masses in a lab, like Marcus's little beads. How would they interact? They interact through a unitary evolution, which is just a time evolution of the Newton operator. Okay, the Newton operator is a two-body interacting thing. Hats are on operators in this slide and probably this slide only. In particular, this left picture is a reversible interaction. It's unitary, and it's entangling. So psi1 and psi2, if you prepare them in a product state, will evolve generically into a non-product state or an entangled state. So what would an alternative look like? Generally speaking, and actually there's some pretty good results that show that this is the only thing that could happen, you have to imagine that if gravity is going to violate that structure, it's going to have to look something like this, where there's, say, your two masses, and then there's some sort of bath or ancilla system that acts in a way such that gravity, as viewed on the two masses, is non-unitary. You can further construct it so that it's non-entangling. So this Schrodinger equation I'm writing down here is an example. People sometimes call this like a Schrodinger-Newton or all kinds of things. This is an example where, because there's an expectation value in the denominator, these are one-body interactions, you cannot entangle things. So gravity would not entangle. The dW is a noise term, which has to be there to make this thing have self-consistent dynamics. So, and that in particular is what gives you this non-reversible nature of the interaction. So this is very high level. I'll give you two examples of what this actually has been proposed to look like. So this is a nice thing that's been developed. So I'm writing this in a very phenomenological way just to make it simple. So imagine, I'm going to use this framework as we go. Imagine I have some detector system, electrons and stuff. It's definitely quantum mechanical. I put a hat on its Hamiltonian. I have to couple it to gravity. How do I couple it to gravity? Well, here's two simple options. One, I couple it to quantized gravitons. Or two, I couple it to some classical gravitational field, which in general I can draw from a classical probability distribution. In fact, you have to be able to draw from a classical distribution to make this consistent. So, there's this well-publicized set of papers by John Oppenheim and his group that are implementing a version of this which is more sophisticated than what I'm showing, but boils down to this for predictions. Okay, and so then the question is going to be, how do I distinguish these two models in some experiment? Here's another example. This is something we've been working on in my group recently. That's why I like to show it. This is a little out there. Maybe you've heard of this idea that gravity could arise as an entropic force or a thermal force. So this idea goes back to Ted Jacobson in 1995, and then Eric Verlinde had this sort of infamous paper in 2010. Okay, so the mechanics of this is, the concept is simple. So think about ideal gas between two movable walls in a chamber. Okay, the walls can move, so they have some distance. It's a degree of freedom. They have a force on them. Why? Because the gas is pushing it around, right? Okay, how does that force arise? The force arises by taking, well, one way of asking how it arises is you say how many microstates of the gas can exist at a given separation x. And then I say, well, thermodynamically, the gas will want to maximize its entropy. So the maximum of the entropy involves a derivative of the entropy with respect to x, and you can work out a formula for the force, the entropic force on the walls, which is given down on the bottom. Hopefully it was very familiar. It's just the ideal gas law. Okay, this is one way of deriving the ideal gas equation of state. So the point here is that the force between the walls is not coming from quantized anything. It's coming from literal atoms banging around in a thermal state. It's very different than, say, virtual graviton exchange. Can you make it actually work for gravity? The answer is yes, at least in the Newtonian regime. Okay, so this is a paper we just wrote up this year. This took many years to get working. I won't go through all the details, but I just want to highlight the point that you can construct a model where the Newtonian gravitational potential arises this way. So there's actually a number of models in here. The one I'm showing is, you say, I have two masses. Those are like the walls. I have a bunch of qubits, which is just some placeholder for gas molecules. And then you couple the qubits, this thermal system of qubits, to the masses in a very peculiar form that took a long time for us to guess, but it's just some explicit formula, okay, with two free parameters in it, two length scales lambda and L. Okay? And then the point is that if you take this model, you say, okay, the qubits are in a thermal state. What's the effective motion of the masses? The state of the masses evolves under some Lindblad equation that's given down here, so that rho is the rho for just the two masses. There's a Newtonian potential that comes from the thermal average of this interaction with the qubits. And then there's some noise terms, which have a clear interpretation, right? So the gravitational force here is given by things randomly forcing the masses, and so there's some random noise in the Newtonian force. And so these noise terms, I'm not writing them very explicitly, but they also involve g newtons and m's and so forth. So just to emphasize again, this thing is a model where gravity comes with noise. It's not reversible, so is Jonathan Oppenheim. So these are examples of these sort of non-quantized gravity models. This is a little bit of a side note, but since Richard went through this whole story about LOCC gravity and non-entangling gravity, I want to personally say that this model is not LOCC, and it violates this whole idea of like there's either a classical model or a quantum model of gravity. Okay. This is a quantum many-body system. It's fully unitary. It has no violations of quantum mechanics whatsoever, and yet gravity arises in this way that looks sort of classical-ish and noisy in some thermal limit. So I think actually we need some thinking beyond this sort of entangling versus non-entangling dichotomy people have been doing. Okay, so good. So that's just sort of my view on models and what you're really testing. You're trying to distinguish quantum gravity versus those kinds of phenomenologies. So how do you actually do it? Okay, so again, Richard gave me a nice, I have to go through this whole idea, but I just want to make an experiment that distinguishes these. So I said I'd start with graviton detection. This is something that got a lot of discussion in the past 2 years, mostly due to this graphic I'm showing. So this is a proposal from Igor Pekovsky and his group. The claim here has been that, the idea here is I make a device that is sensitive enough that it will click when one graviton is absorbed by the device. And that is possible, no doubt about it. The question is, what does that have to do with testing quantum gravity? And I'll talk about that next. Let me show you how the device would work. This is similar to what Ralph was getting into, actually. So instead of using light, they propose using a Weber bar. Okay? The Weber bar is just a piece of metal. Say you can cool some mode of its vibration to the ground state and then measure single phonon transition. So if the bar goes from the 0 to the 1 phonon state. Gravitational wave hits it. If the wave is strong enough, it'll make the detector go from the 0 to 1 phonon. I detect the phonon and I say, I've detected a graviton absorption event. And indeed, that would be a totally consistent interpretation of this if you got it to work. However, if you're wanting to test is gravity quantized, the question you have to ask is that experiment distinguishable from a model where just a classical gravitational wave hits my quantum Weber bar? And the answer is no, in the following sense. Okay, this is an old story in quantum optics where people were arguing about, does the photoelectric effect prove that the photon exists? The answer is also no, contrary to what you may have heard in school. So here's the argument. This is due to Roy Glauber in the 60s. So think about E&M, so electromagnetic light shining on a semiconductor or a metal or whatever, something with a work function. So what happens? So you know that there's bound electrons, there's some gap for energy such that the electrons become conducting. You shine the light, you ask when did the electrons start conducting and at what rate? And what you can do is, this is a little textbook exercise. You open Sakurai or whatever book is used in Europe to learn quantum, sorry. And you just calculate what's the transition rate for the electrons to start conducting as a function of the intensity and frequency of the light I'm shining. And you can compare it in two models. One where you quantize the electromagnetic field, that's A with a hat, and one where you don't, you just make it a classical random variable. And you can ask, what are the different answers? And the results is that the answers are the same. So to explain the single electron click events can be done perfectly well with a classical electromagnetic wave. You also get these sort of famously, supposedly quantum effects, like there's a step function that enforces that the frequency of the light has to be above the gap of the detector. That also comes out classically. It's just a resonance condition. The intensity comes in the same way, and there's this detector efficiency that's, again, the same. Okay. So what I want to say here is that, yeah, you can make a detector that you could interpret the events you'd see as detecting graviton absorption events. However, you can just as well interpret them as just power incident from a classical gravitational wave. So that experiment would not really tell you anything about quantum gravity. How much time do I have? 15 minutes. Okay, so I can say a bit more about this, but I think I'll punt it to the end if anybody wants to hear it. I think the conclusion should hopefully be clear. That's the thing I'm not going to talk about. Okay. So then that's a sort of maybe a negative conclusion if you want. In fact, I started thinking about that because I wanted to say I could detect gravitons and find quantum gravity. So on a more positive note, I want to talk more about the stuff that Richard was talking about this morning, which is tabletop tests in the Newtonian regime. So can you detect the entanglement generated by the Newtonian field? That's now a very hot topic for many years now. So here's my reconceptualization of how Richard was explaining it. So on the left, again, quantum gravity, normal quantized gravity, Newtonian operator, hats, entangles, reversible. Right side, as an example, here's this sort of semi-classical model where gravity does not entangle and therefore is non-reversible. How do I distinguish these? So there's many ideas out there. I think the one that people are most familiar with is this one by Bose and Marletto and Vidral, where you'd have diamonds falling in a lab. Roughly speaking, what you want to do is have two systems. So here your mass is this diamond. The diamond has a nitrogen vacancy. Basically, this is just a big neutron. Okay, so it's a neutral, electrically neutral object with a somewhat large mass with a spin that you can control that couples to the mass. So in particular, you can take this thing, put it through a magnetic field gradient. It'll superpose the state of the diamond. Supposedly, no one's done this yet, to be clear. Okay. And their specific proposal was you do this twice. You have two of these diamonds sitting next to each other, and they're in this configuration where each diamond is on 2 paths. So there's some sort of differential lengths between the pairs of paths. Because there's a spin, it's very easy to think about how this works. Okay, it's just 2-state systems now. So the evolution of the joint state, if you say it starts in some initial register, you superpose it, it falls, L and R represent the left and right paths. Okay. Again, assuming gravity is quantized as usual, what would happen is that this state evolves into some non-product state. It's an entangled state where the entanglement, sort of amount of entanglement, is controlled by this e to the I phi phase, relative phase. E to the I phi, the phase is just the Newtonian potential multiplied by time. And usually it's written in some expansion where I assume that the distance d between the 2 diamonds is large compared to this superposition scale that I'm making. To observe it, you want phi to be sort of order 1-ish. How hard is that? Okay, it's pretty hard. So these are numbers that I pick myself. They're roughly based on the Bose paper. So if the diamonds are nanograms, you can't put them any closer together than about 1 millimeter, otherwise Casimir forces and worse things than that start happening. If you superpose them at a micron, so it's a Schrodinger cat separated by a micron, to get an order 1 phase, you need this to operate for sort of 1/10 of a second. And by operate, what I mean is these diamonds are falling somewhere in a drop tower, and you need nothing to happen to them for 1/10 of a second. You can't destroy this sensitive entangled state. So it's pretty difficult. I'll show you how difficult it is in a slide. But supposing first that you did this, what do you learn? So it's typically said something like, if I do this, I rule out all the non-entangling gravity models, and that is correct. Okay. But I want to, again, promote a little bit of a twist in this story recently, which is that it's a little more subtle than that. You can make these models that are not non-entangling but not fully entangling. So this is an actual prediction for such an experiment. Okay, so let me walk you through this. So what do I measure at the end? I should have said. How do I know this is entangled at the end? I do a Bell test. I do a CHSH measurement on the spins. Okay. The Bell test tells you that the state is entangled if some certain quantity, like this spin correlator, is above 1. So x and z and y, okay, those are the Pauli operators on this LR basis. They're just normal Paulis. You can measure this thing in the real lab. There's a theorem, if the absolute value of this thing is above 1, then the state of the diamonds has to be entangled. So that's the goal. You want to see W above 1. So it's true that if you see W above 1, you're going to rule out all of these non-entangling gravity models. So for example, Jonathan Oppenheim's stuff was constructed such that it's not entangling. Okay. On the other hand, there are now these models, like these entropic models, where it's more sophisticated. There's actually a free parameter that you can tune that changes how much the gravitational field can entangle things. And so what I'm showing here on this plot is, as a function of time in that Bose experiment, what would this quantity do? So in the thick black curve is normal quantum gravity, and then these dashed lines are various entropic models, where you can see that I can sometimes get this thing to go above 1, and so it's entangled, but it's sort of not fully entangled, or it's less than 1, and so it's not entangled. Okay, it's a little more subtle. So actually, the interpretation of one of these entangling experiments, I think, is a little more sophisticated now because of existence theorems of such models. Nevertheless, it would rule out all of the classical, these like non-entangling gravity models. Okay, so this is again more towards what Richard was saying. So how hard is this? Okay, these are gnarly experiments. So how hard would it be to see this order 1 phase in a real experiment with diamonds? I was emphasizing what I need to do is have the diamonds falling in isolation such that this state, the entangled state you're generating, isn't decohered. So one of the many things that would decohere such a system is just gas. Okay, you're going to do this in vacuum, but there's no such thing as a pure vacuum, right? So real vacuum still has a little bit of residual stuff in it. And if I estimate, say, how often does a gas particle hit one of these diamonds, if a gas particle hits the diamond, right, then it measures where is the diamond and you collapse these sort of left-right superpositions. So just a simple estimate of the rate for that would be something like this. I say I take the best vacuum that's ever been definitely measured, I would say. It was something like 10 to the 14 torr. I mean, I think owners in here somewhere would agree with me that that's an aggressive number. Let's put it in a cryo chamber, so it's cold flow gas. And you ask, what's the gas collision rate? It's still something like 100 megahertz. And I needed this thing to go for 1/10 of a second. So this is a wildly difficult piece of numerology, right? You're having way too many gas collisions for this to work. My personal interpretation of that result is that you want to think about maybe a variation of this specific setup, or you need to, well, you probably need to think of a variation of the specific setup. Also, you just need to think hard about, how well can I engineer these systems? Can I go to space and do this or something? Okay, so I'm actually quite optimistic that one of these entanglement experiments happens in my career. However, it is definitely worth thinking about other options, and so Richard presented some, and I think Owner is going to give a talk later that's a related sort of different idea using torsion balances. Okay, so I think I have like 3 minutes or something. I want to, great. And then I'll have questions. Excellent. So the last idea I want to pitch is, I'm kind of trying to emphasize that as exciting as this stuff is, these experiments are all brutally difficult. Okay, so I would like to end on a most positive note I can, which is, what's an experiment that's less brutally difficult? So we've been emphasizing this checking if the field entangles, checking if the interaction entangles. But what I haven't emphasized is this idea that if the field doesn't entangle, it has to be a non-reversible interaction. There has to be some noise acting on the masses. And so you could do an alternative thing, which is just look for this noise. And this is actually quite an active idea. So let me give a concrete example using this entropic model, just to give you a sense of numbers. Let's say I have the Earth. I have an atom interferometer, which we're going to hear about in the next talk, so just atoms superposed in two locations over the Earth. Okay. If in this entropic gravity model, or generally in these models where the gravitational field is a stochastic random variable, what's going to happen is the Earth's field is no longer perfectly coherent. It sort of fluctuates a little bit. So that'll cause fluctuations on the atoms, and they'll decohere. So what that means is if I take the atoms, I superpose them, and I try to put them back together, I won't see the contrast fringes because the state got killed in the middle of the experiment. So as a concrete example, if you take that entropic model, it predicts a definite rate for the decoherence of the atoms. So here, d in the denominator is the distance, in this example, from the center of the Earth to the atoms, some big number. Delta x is the separation of the atoms. Lambda and t are free parameters of the model. The numbers you insert are this experiment from Stanford that was done. So the experiment in Stanford, it's a large atom interferometer. The separation of the atoms is about 0.5 meters. It runs for about a second. So you can say, well, we did this experiment already. I didn't see the atoms decohering, and that sets a bound on how much noise the gravitational field is acting with. And this is a quantitative version of the bound. And something I want to emphasize is that if you take these models sort of at face value, they tend to come with predictions that are sort of in the range of things you can already go look for. So in this example, with lambda equals 0, which is a technical thing, the decoherence rate it predicts is 10 hertz. So that's already ruled out by the Stanford experiment. So then you have to tune this parameter to move it a little bit. Okay, but this is something that is already happening experimentally. So I like these noise searches for that reason. I want to end with like a sort of open question or a call to arms maybe for people to think about. So in terms of the cleanliness of the interpretation, if you're looking for gravitational noise, it's a very difficult thing to say, I saw noise in my experiment and it's from some weird quantum gravity model that Dan Carney cooked up. Nobody's going to have that interpretation. Right? You see noise in an experiment, it's my laser was messed up or something went wrong. So what you really need to do is rule out gravitational noise. So what would the logic be? Again, I'm trying to promote this idea that any model where gravity does not entangle things has to have noise. There's a nice theorem actually by Flaminia and collaborators on this. And quantitatively, there's these older results. Richard mentioned Caffrey-Taylor, and recently Angelo Bossi and his group had a nice version of this, that say something quantitative. So if gravity is not entangling, then it must produce a certain amount of noise, which can be quantified in various ways. So I'm showing the Caffrey-Taylor picture, which is I have a torsion balance, and I think I have another torsion balance not shown. So there's one on top of the other. And they quoted some bound that says, the variance in the angular momentum must increase at a certain rate, which has a g Newton in a little g. Okay. This Bossi thinks is something similar. There's some sort of rate of noise addition that, again, depends on the Newton constant. Okay. And so the idea would be, I go do experiments. I see that they're noiseless to a sufficient level that I can rule out the existence of this noise. Then I'm also done. Then I've basically done the same thing as a gravitational entanglement experiment, because I've ruled out all the non-entangling models. So it's really an alternative strategy that I think is just as good, philosophically. But I think there's sort of a lot of good open questions about what's really the classification of all of these non-quantum models to work out. So the interpretation here is not totally fleshed out. Okay, so I'm done. So I want you to take away from this, in this sort of testing quantum gravity model, I think you should have the null hypothesis in your mind that gravity is quantized. It's a perfectly reasonable guess. What if it's not? Then, okay, it's not graviton, sort of by definition. What is it? Okay, maybe it's thermal, maybe it's fundamentally classical. There's plenty of other things people could conceive of. Plenty of room for new models. Can you detect single gravitons? Yeah, actually I think the answer is just yes. I mean, no one's done it quite yet, but there's plenty of ways of thinking about this that are not crazy. However, if you do it, it doesn't teach you anything about gravitons, somewhat paradoxically. Can you detect gravitational entanglement? Yes, very clear interpretation. However, the experiments are very, very difficult. And then in this last sort of option, can you detect anomalous gravitational noise? Yes, people have already tried. However, the implications are not fully known yet. All right, thank you very much.
Thank you very much for this clear talk, framing how one can interpret this kind of experiments. Successfully, so we have time for questions, Eduardo.
Okay, sure.
Hi, thank you. Oh, hello? Is this on? Yeah, I think so. Okay, nice. Hello? Oh, no. Yeah, thank you very much. I mean, this perspective is very nice, and sometimes it's not that often that you see it. Like, people love making claims. Well, one thing, I guess, one comment that I would make is like in the entangling model that you consider like entangling gravity, and you wrote, you call it, I forget what you call it, like quantum or
interpretive quantum gravity.
Something like that. So one point that I want to emphasize is that what you wrote, though, the hats on what you wrote, the phase space that's quantized is the center of mass of the masses. There is no Hilbert space for gravity here. So in what you're doing, in that particular way of modeling it, one question that's important is that, okay, in what sense is this proving that gravity has actual quantum degrees of freedom, which is a sentence you use, or is it okay if what's quantum is matter, because you quantize matter, and then you can talk about superpositions of the field, but then again, the hats are on matter, right? We've done some work on these kinds of things, right? And the idea that you can have relativistic retarded potentials and still get, there's an extra hypothesis, which is there's a mediator going on. So there's an extra assumption that goes into that kind of experiment of entanglement, gravity-generated entanglement, right? Mediated entanglement, which is the fact that you assume that there's a mediator theory. Because if you have a contact model, you can still have entanglement generating, and you never need to quantize gravity. Not saying that that's what I believe it is, right?
Sure,
but,
sure, yeah.
Just,
yeah, no, thanks for the question. This comes up a lot, and this is a nice, precise version of it that I can answer because I made a slide. So, I agree. Okay, so let me say it this way. I agree that you would need an extra assumption to claim that from the entanglement experiment, you know that graviton is there. So you can actually say what exactly the assumption is. Oh, where did I put this? Yeah, okay, good. So you can prove some theorems. And there's also some nice heuristic results from Bob Wald and people. So here's a little theorem you can prove in scattering. Okay, so if I have a model where there's two-body scattering, which is unitary and Lorentz invariant and has a 1/r interaction at low energies, at low velocity, excuse me, that has to have gravitons in the final states.
I can do a Pauli model for that, a contact interaction, and still not violate the theorem.
I don't, what's that mean?
Okay, we can talk about
Yeah, we better talk later. But to be clear, I mean, yeah, so this is a thing you can prove, and the way you prove it is kind of interesting, okay? So what I do is I calculate the scattering amplitude for two-body, just Newtonian scattering. I get the normal, the usual 1/p² answer, and then I say, oh, this has to be from a Lorentz invariant model, so there's a 4-vector that became a 3-vector. And then I say, I look at these amplitudes, they have to obey unitarity, so that's Lorentz invariance. How do I do unitarity? I say unitarity means that there's an optical theorem. I have to be able to take the forward scattering amplitude and express it as a product of amplitudes through this formula here. Okay? And if you apply that to some simple process in such a model, there's a pole in the propagator in the middle that says that you have to have, so this dashed line would be sort of the Newtonian interaction if you want. I have to be able to cut the line, and there's some final state that radiates out that has to have the properties in order to make this equation work, that there's a g Newton in the coupling, it couples also to the mass in the right way, and it has to be a massless boson coming out. So
there's an extra assumption that there's a field, there's a medium.
no, there's not actually. This is straight from S matrix theory. Yeah. It's yeah. That's why I wrote the paper, because people were saying this mediator stuff so much, and I'll show you. Okay.
So before we have, maybe let me just say one thing, which is that there's a little bit of an advertisement. So you see, this is a perfect example of something where some structure debate that we are considering for the RQI cost action could be, a good format to discuss these things and to improve our understanding. And just as an advertisement, today after the afternoon sessions, there will be the meetings of the RQI cost action working groups. And one of the points that will be discussed there is, possible structure debates. So if you are, interested, join those discussions after the afternoon session. So we have time for more questions. We have plenty of them, so maybe we won't be able to take all of them. Harris.
The starting point in the thank you. The starting point in the quantization is not so straightforward. I mean, it's standard in the sense you expand the metric around Minkowski. And you assume that Minkowski's metric is classical, no fluctuation, and so on. So this is an additional assumption for standard quantization. So
Yeah. Sorry, you want to?
I just want to make it for reference, this point. And the second point, you might be interested at very low temperatures. The standard formulas for the coherence may not hold. You might need, so it might be less decoherence than the usual models. For example, the models by Chen use for scattering predict.
I'm definitely oversimplifying that estimate.
Yes, but it's quite possible that at sufficiently high temperature, the coherence is highly suppressed. But somebody has to do the first principles calculation. Good. That's what I want to say. Okay.
Yeah, maybe let me just, regarding the first point about background dependence, so I want to make clear that I'm thinking we should do these experiments specifically because there are such assumptions built into such a model, right? So to be clear, I'm in agreement. All I want to say in that slide is that you can make, once you are in that regime, that model makes predictions. Does a model actually reduce to that regime? Actually is an open question.
Just that there are other theoretical possibilities beyond that.
For sure, absolutely, yeah.
Thanks a lot for a nice talk. I actually have a question and not a point.
Grazie.
You were mentioning a lot this notion of entropic gravity.
Yeah.
If I did not miss anything, you never specified the models. My question is, to my knowledge, many entropic gravity models are ruled out from cosmological observations. So which are the ones you considered, and are they already ruled out or not?
Yeah, thanks for the question. I gave the citation, and I'm happy to give you the slide. So we wrote a model this year. I personally wrote one down, which is not ruled out. We were trying to find one that's not ruled out.
you showed the Lindbladian evolution equation. So what is the typical Lindbladians you assume?
Oh, yeah. So, okay, well.
This is a random guess, I would say.
No. So you write down in a very explicit coupling of these qubit mediators to the mass. It's a totally concrete formula. You couple the qubits to a heat bath just so you can keep things.
No, I understand. But what are
and
the
then
jump
you
operators you assume?
and then you derive the Lindblad operators. They're derived from that structure. They're not assumed.
So they are like photon laws or decoherence, or what are they?
They basically do position measurements. Right, the gas is colliding and seeing where it is.
Well, in the gravitationally induced entanglement experiments with the diamonds, the masses separate, they're supposed to entangle, and they're very difficult. What do we know about electromagnetism inducing entanglement in this way? It seems to me that we should be interested in this because they should be much easier to do and they would be a natural calibration point. Can you comment on that?
Yeah, I would love it if someone did a very direct analog of that experiment with ENM. It should be plausible. I don't see why it would be that hard. I would say that the electron double slit essentially does this if you think hard about how the electron is detected by the screen.
Well, but it's not directly the same thing.
It's not as clean, I agree. Yeah.
So, okay.
Yeah.
Next speaker again.
Le batterie del microfono sono morte, quindi adesso lo cambiamo.
Oh, I have this thing.
Anche se puoi usare quello da tavola, anche quello, sì, lo accendiamo.
Okay. Can you hear me?
Okay, so.
This is dying.
Okay. Very good. So.
Does it?
Yeah, now
Can you hear me? Can you hear me? Yes. Okay. So I have to.
Okay, so let me introduce you first.
Yeah.
So the next talk will be by Gabriele Rosi from University of Florence. And so we've heard all these talks about interesting proposals.
Okay. So I'm very happy to be here in order to speak about. Sorry. Let's try again. This is. Okay, again. So, okay, I try again. So, I'm very happy to be here to talk about our atom interferometry measurement applied to gravity measurement. I'm Gabriele Rosi from INFN Florence Division and the University of Florence. So, my talk, which is as you will see, a very experimental talk, is divided in two parts. First of all, I will speak about our ongoing efforts in doing G measurement with atom interferometry. I will give you motivation. I will talk about previous G determination with this technique and the accuracy limits. And then I will illustrate our new scheme in order to push the accuracy of this measurement towards the state-of-art level. And then I will explain the status of the experiment and the prospects. In the second part, I will give you an idea of what we want to do with positronium atoms, so a weak equivalent principle test. And again, motivation, I will illustrate our proposal to measure gravity fall, gravity acceleration with positronium atoms. And then I will give you some results from simulation. Let's start with big G, which is a very hard measurement. As you can see here, in the past, several determinations has been done, but the discrepancy between this kind of measurement is very large, up to 10 sigma, I think. Another interesting thing in this graph is that I did not update it from 6 years, because in the last 6 years, no new G determination has been done. So it's quite a problem. This is a classical measurement. So
just to give you an idea. So why a big G measurement, a precision big G measurement is difficult? Because gravity is weak. It cannot be screened. There are several systematic effects, so they can perturb the determination. And more importantly, it's not easy to generate a very accurately known gravitational field to be tested. And moreover, G has gravity itself is isolated constant, so you cannot, there are no connection with other fundamental constants. So why atom interferometry for measuring big G? Most of the determination with big G has been done with classical instruments, basically torsion balance. So they are an advantage version of the torsion balance used by Cavendish. So the idea here instead is to use cold atoms in an atomic fountain as a free-falling microscopic masses. This is very important because basically it's a free-fall experiment. There are no mechanical parts to be characterized or that deviate from ideality. And it's also very easy to model, at least the probe, because it's a point-like particle. So the only things to take care is the source masses. So our instruments, as you well know, is atom interferometer, which is, I will give a very brief introduction. Maybe you know very well how does it work. But in any case, is basically with respect to a classical laser interferometer, here the role of matter and light are exchanged. So the idea is to start from a wave packet, split it in two parts with a laser pulses that provide a momentum transfer to one of the two wave packets. Then you leave the arms open, and then you recombine with mirror pulses and another beam splitter pulses called pi/2, and then the wave packets they are still again in superposition, and they interfere, and you can reconstruct interferometer fringes by measuring basically the population of the atomic population in the two interferometric arms. And this is the basic formula when you can see the connection between the phase shift that you measure with the K effective of the light and the free evolution time. How to use this instrument for big G measurement? Basically, we need two interferometers in free fall. What? Again? Okay. Can you hear me better? Okay. So the idea here is to use two interferometers, so two atomic samples, which are vertically displaced by a certain quantity, usually tens of centimeters, and perform simultaneously two atom interferometers in order to measure the difference in phase shift and therefore the differences in acceleration between the two atomic samples. Then you have a measurement basically of the gravity gradient, of the local gravity gradient. Then you can modulate the gravity gradient with external source masses and basically performing a double differential measurement. So measuring the gradiometric phase shift in one configuration, let's call far, and the other configuration, let's call close, you can isolate the contribution of the source mass gravity field from the contribution of the Earth, and then provide an estimate of the value of G. This was done 10 years ago with this technique, reaching a final sensitivity of around 150 ppm. Okay, thank you. So, if you look at the error budget of that experiment, you can see that the limiting factor is due to basically to the size of the atomic sample that we are using in order to prove the gravity field. yes, the single probes are point-like particles, but the overall collection of atoms has a spatial distribution in the order of a few millimeters, 1 centimeter. So we need to, was the current limitation to the last big G experiment with atom interferometry for G determination. No other experiment has been done so yet, up to my knowledge. And this has been recognized also by CODATA, and unfortunately 100 ppm is not presently competitive with the best torsion balance measurement. We have to push towards the 10 ppm level, which is not trivial, I must say. So there are two possible approaches. One, you can squeeze your atomic sample in dimensions, make it cooler, but this is one possibility. The other possibility is take the cold atom technology of the cold atomic fountain and try a new method to minimize the error, maintaining, I mean, the same technology for atom manipulation. Most of the problem related to the cloud dimension and geometry distribution of the atomic sample is due to basically to the gravity gradient that we have, for example, gravity gradient of the Earth. And this is something that you can see from the first formula, because you see the gradiometric phase shift is directly connected to the distance between atomic samples. So that means that if you want to do a 10 ppm level determination, you need to control the distance at the level of few microns, which is completely is impossible experimentally. In our old experiment, we used tungsten source masses in order to create stationary point in the acceleration in order to easy to surpass this issue. However, the problem is not solved completely. We shifted the problem from the position of the cloud barycenter to the vertical extension of the atomic clouds. Another approach, inspired by one of the Albert Rural work, is to basically, instead to try to measure accurately the distance between the clouds, is to cancel the actual gravity gradient signal at the first order, so the linear part of the acceleration profile that the atom are probing, with, I might say, a trick. Simply, it's possible to demonstrate that it's possible to introduce in the signal, in the gradiometric signal, a very well-known gravity gradient, fake, I must say, gravity gradient, simply by perform a frequency jump during the pi pulse. In this way, we can get rid of the linear part, and we know very well what we are introducing, since it's just a frequency measurement that we have to do, and we can do it very precisely. And then what is left is measure the residual phase from the nonlinear part of the gravity profile. And this is the idea of the new experiment that we are setting up in Florence. The idea is the following. We have two configurations, with and without given source masses. Source masses must be large enough in order to produce in a, half meter, in a large region of space, a quite linear gravity gradient. So we perform always the double differential measurement with and without source masses. And we compensate at the level of few percent the linear part. So this can be done offline, basically. And then our measurement is just to determine, we perform the measurement just to determine the residual phase shift at the level of 10 ppm. But in this case, the residual phase shift is much less sensitive to the position and distribution of atomic sample. This is an idea of what the source mass is that actually has been produced. The geometry of the source mass must be simple, so we use basically a ring. good degree of homogeneity, high density if possible, and at the end of the story, what we choose for our source masses is with giant ring. You can see the dimension, 1 meter of 1 meter of diameter for a total mass of 5 tons. And then we have to use this object and we need also a way to lift this object away from the interferometer region and then put it back. So what I'm talking about is not exactly a tabletop experiment. However, you can see from the graph that it is possible, choosing the right geometry, have a half meter where the punctual gravity gradient is constant within plus or minus 2%. We did a simulation in order, first of all, single particle simulation, in order to prove how well we are independent from geometric factor of our atomic sample. And you can see here, I want to point out just the baseline shift. So if I change the baseline of 1 millimeter with this technique, I have only 50 ppm of systematic shift. So I gain a factor 100, simply implementing this scheme. All right, we analyze also the full experiment with a Monte Carlo simulation. We choose experimental parameters that are realistic in terms of position, sites, temperature, and so on. And we try to also several levels of compensation of the gravity gradient with the Albert technique. Okay, so the results of the simulation are very promising, since the shifts are mostly zero with our span of parameters, and we have to care about only of transversal temperature atomic sample, but it seems we are inside the 10 ppm target of our experiment. So this is something that we are very happy about. So we also care about the statistic, because in order to perform a gravity measurement, a precision measurement, you have to integrate a lot. In the previous experiment, the required time to reach 100 ppm was 100 hours. We have to improve also the short-term sensitivity. And what we have done so far, using the old apparatus, is there are several methods in literature that claim you can improve the sensitivity of atom interferometers. Most of them are proof of principle, where not all of them, most of them are proof of principle where you can prove that you can split up to several K the atomic wave packets. But this is as a cost. The duty cycle is much slower, while I would like to have 1 Hertz of duty cycle, so very fast. So the idea here is to explore a new transition of rubidium-87 using blue light in order to gain a factor 2, which is not so much, but I think it's very robust, since we are dealing always with Raman transition. We don't change the way of the measurement, we don't change the recipe. It's just a change in the transition that we are using for Raman. And we did some preliminary results. As you can see here, yes, our sensitivity is slightly below what we can achieve at 780 nanometer, but this is basically limited by technical aspect that basically laser power that can be solved with some work. So I think this is a good idea to be implemented in our apparatus that after several years is under construction. Since we have to lift up these 5-ton source masses, we need a lifter, and this is the CAD of our quite large apparatus. you can see we have the positioning accuracy that we require for the source mass is at the level of 50 micron, which is challenging, but is possible with the current technology. And here you can see the source masses has been realized in steel, and you can see that the work are in progress for the realization of the experimental infrastructure. So, conclusion is that yes, it's possible to perform at least at 10 ppm level a G determination with atom interferometers. Sorry, it's not exactly a tabletop experiment, but at the end we are realizing, and I hope in the next few years to have some results in terms of big G accuracy and so on. So now I switch a little bit the topic, and I'm going to talk about another activities of our group, which is the weak equivalent principle test with positronium atoms. So instead to use stable atoms like rubidium, we are going to use these very exotic atomic species. What are the motivations for such kind of test? As you well know, there are two pillars in modern physics, two main symmetries at the quantum level CPT, at the macroscopic level the Einstein equivalent principle. Are expected that at the Planck scale something must happen, symmetry must be broken, and the idea is to try to performing, for example, with antimatter weak equivalence gravity test, is possible to see if there are some residual at low energy of this high energy symmetry breaking. So, and this can be important in order to explain why universe is matter dominated instead of antimatter dominated or equally dominated between the two. This is an open question in the modern physics. I want to point out to this landmark paper, which is the first time from the Alpha collaboration that they have measured the free fall of anti-hydrogen with extreme, for the field with an extreme precision at the level of 10–20%. So this is important to remember how difficult are these experiments. But since we have already experiments that are using anti-hydrogen, why positronium? There are three reasons to me. First of all, it's intrinsically different from anti-hydrogen because it's made by point-like particle, just electron and positrons. 50% of the positronium is antimatter. This is not true for the positronium. This is not true for anti-hydrogen, which is most of the mass is due to the color field. And also it's possible to relate quite easily, according to some theoretical paper, from, for example, this one from Kosteleski, it's possible to relate violation with parameter of the standard model extension. So there is a direct connection between theory and experiment, I must say. So this is basically the target, the goal of the Q+ collaboration, which is it's involved by INFN, University of Florence, and led by Politecnico di Milano. I want to show you in this movie what we would like to do, if the movie works. Of course, does not work. Maybe. Okay, I skipped the movie because for some reason it does not open. Sorry. So, but I have this backup slide. So the idea is to do. We have to produce the positronium. We use positrons from beta plus decay of sodium 22, And we have a converter, a tungsten plate covered by monolayer of sodium, and we produce PS minus ion, so positronium with 1 electron. It can be accelerated, so the experiment is horizontal, okay, horizontal direction. Is accelerated, then we have to get rid of the electrons with a photodetachment scheme, and then there is a preparation stage for the positronium from n equal 1 and n equal 2, because the positronium, I forget to say, positronium lifetime is very short. It's 100 nanoseconds, 150 nanoseconds. If you put it in n equal 2, you extend it at 100 microseconds. And then we have the Mach-Zehnder interferometer that now what I'm going to illustrate is our work on photodetachment cavity and Mach-Zehnder interferometer, while the production of positronium atoms is from Politecnico di Milano. But just to tell you how things work, so this is just a picture of what is needed in order to accelerate and produce and accelerate PS minus. So we have this converter, tungsten, coated with one monolayer of sodium, and in this way has been demonstrated that from the surface PS minus can escape. Then you have this very tiny acceleration stage. Since the PS minus lifetime is only 500 picoseconds, and then the idea is to accelerate towards and focus in a hole of 1 millimeter, and to give to the PS minus an energy of 300 electron volt. And then this flux of PS minus is ready for the photodetachment. Photodetachment, we did a Monte Carlo simulation of this stage. We would like to use, an enhancing cavity, linear cavity, with a waist of 1 millimeter, and we explore different wavelengths. 1.5, it's a micrometer is, the wavelength commercially available, basically, and then the best wavelength that we can have is 3.6 from a scientific point of view, because it's near threshold, and the electron recoils in this way. It's very tiny for the positronium. And also we explore what happened if the tungsten plate is a different temperature, or cryogenic 10K, or environment temperature. So we had these results, which graph. What is important to understand is that photodetachment can be very efficient, even if half of the PS minus are unfortunately decaying. And then what is important is that the flux that we can obtain, the positronium flux that we can obtain, is at the level of 10 milliradian collimation, which is not bad, I must say, also with the 1.5 micrometer laser. A temperature play no role if we photodetach at 1.5 with the 1.5 micrometer laser. So I have 5 minutes. So after that, we have another stage. I will not go into detail. Here you can see the scheme, the energy scheme of positronium. Then we have to excite using an UV excitation stage, and then a microwave stage, in order to bring the atoms to the 2s1. And in these fundamental levels, we can perform atom interferometry using 1.3 micrometer laser, which are commercially available. So they are, and you can have also a powerful source of these lasers. So this is the scheme of our Mach-Zehnder interferometer. It's a single photon, it's simply a single photon interferometer that it's now usually used with strontium atoms. Instead to be in time is in the space. So you have a pi over 2, several pi pulses to open the interferometer, a pi star pulses, which is a trick in order to maintain one arm in the fundamental state, while the other arm of the interferometer is from the excited state is put in the fundamental state. Then you have the free evolution time, and then other pulses and other pi pulses can recombine and close the interferometer in the horizontal direction. The idea here is to use a single photon transition in order to imprint this momentum to the atoms. And this is, we will see it's very convenient with respect to other approach, old approach based on basic Bragg transition or just optical grating. So these are the pulse characteristics. I don't want to comment so much here, but I want to show you that the required power for the experiment are within the feasible. So nothing that we study the interferometer efficiency according to the transversal coordinate, to the angles of the positronium atoms, so the divergency of the positronium atoms, and the energy of the positronium atoms. And regarding the detection method that we want to implement, usually in atom interferometer, you have to detect the two arms in order to normalize the population. Here, instead, we want to get rid of one arm and just try to select the atoms that are basically going straight to the interferometer. So we expect to see interferometer fringes. We lose the possibility to population normalization, but this is not a big deal because we expect very few particles at the end of the interferometers. So at the end, these are the simulation results in terms of integration time. Now, what is interesting here is that, yes, you can have, accordingly, of course, with 1 milliradian of divergency, you can have the results of 10% after a few days. But what is interesting here is that also with 10 milliradian of divergency, which is feasible, we demonstrated that is feasible, you can have delta G over G equal 1 in 2 weeks. This is not bad, I must say, as experimentalist. And this is, much more, interesting than anti-hydrogen, since what I have explained before. We also make a comparison with what is present in literature regarding T-scheme from the very old paper from Marcus Oberthaler. And we see here that with respect to the technology of Bragg transition that are used in the Oberthaler paper, here you can have, in terms of time, total time for the experiment, at least an improvement of a factor 100. So it's not very well. So now what we are doing in Florence is we are developing the photodetachment cavity. Our target in terms of circulating power is 200 kilowatt, which is near the state of the art, I must say, for this kind of enhancing cavity. And actually, we have demonstrated 60 kilowatt up to now. The finesse is what we expect. The limitation now is due technical reason. We don't expect bad surprise because I didn't show this kind of analysis in the presentation, but we did simulation regarding the heating process on the mirror, deformation. So we expect to go to the target just rising up the power of the injecting laser. So conclusion is yes, positronium can be used for precision gravity measurements. It's exotic atoms. It's difficult to manage, but it can be much more effective with respect to the standard anti-hydrogen experiment. The next step is to complete the study, the theoretical study, numerical study of the experiment, and make produce and make real the first production of PS positronium atoms at the Polytechnic of Milan with their apparatus with our optical cavity for photo detachment. And I thank you very much for the attention.
To see, what it takes to do this kind of precision experiments. One can come up with proposals, but actually making the experiments is also very challenging. So we have time for questions. Wait for the microphone.
Okay.
And you have to use the microphone.
Okay.
Yes, thank you. Very interesting talk. There are two states of positronium, para and ortho. Does your experiment distinguish, or is it that the short-lived one just decays?
Decay.
Okay, so it's all...
Or it does not exist
okay.
to us. The other,
so it's all just the one?
Yeah.
Okay, I figured as much, but I thought I would ask.
In fact, you transfer it to a longer-lived state, right?
Yeah. The idea is to...
even transfer it to an even longer-lived state, or not so short-lived.
Yes. Usually, in this kind of experiment with positronium, they use the Rydberg atoms in order to extend the lifetime of the positronium towards 1 millisecond. In our proposal, we don't want to use it because the Rydberg atoms are very fragile. So we stay in the lower part. It's a different approach.
I'm excited to see this positronium thing work. I want to make sure I understood the basic idea of doing an equivalence principle test with this. So are you going to just measure little g on the positronium and then just compare it in classical post-processing to some like strontium measurement? Or are you going to do a differential measurement somehow?
Actually, there is, from a point of view, yes, there is, I didn't explain yet, but there is the idea to do a differential measurement because you have an interferometer. One interferometer cannot provide information. You have to do two stages. One with slow positronium, and then another with fast positronium. And then you can, at this point, you have two interferometer fringes, and you can do the difference. So if you look in the detail of the experiment, yes, we know that we need a zero level interferometer. I don't know if I
just want to make sure I understand what equivalence we're testing. The equivalent free fall of positronium in two different speeds, or the fall of positronium versus another atom, or?
Basically, the precision is so low that you don't need to compare. No, this is the reason why we don't need another atoms to compare. It's useless.
Any further questions?
Before I die.
So, well, maybe then I can say, if you have a few. This point you mentioned, I understand that it's to suppress some practical things, the comparison between the fast and the slow. But then the interferometer times are different, or I'm not sure. So how?
Different. The interferometer's time are at least the interferometer times must double at least because you need one section for.
So you try to suppress everything else not connected to the interferometer time.
Yeah.
And then the signal you look for is.
So. No. At least sorry. with different velocity, you change the interferometer time, of course. So you have double the velocity, half of the interferometer time, and then you t square, so it's 3 over 4. 3 over 4. Yeah, any other? Yes. Yeah, you have to get rid of them.
Thank you. So, any other question? Otherwise, we can move to you and start getting your. You will start preparing your talk, and maybe time for a very short question.
Oh.
Coming.
Sorry.
Oh, yes. So, just a second.
Yes.
Just a moment. There will be 2 announcements, but there was a short question.
Thank you. So in one of the plots, you showed that delta G upon G for 3 days kind of time window as well.
Yes.
So are we assuming staticity of Earth's gravity around that time? For example, how much contribution for tidal effects due to moon over 3 days would accumulate into?
Can you repeat? Because
so my question was delta G upon G over the 3 days, let us say, in one run of the experiment where you are doing over 3 days.
Yes, in 3 days with a given divergence of the beam.
Right.
Okay.
But over 3 days, for example, the gravity due to, let us say, moon's passing or tidal effects.
No, it's rejected. It's rejected because the idea is to do 2 experiments. One with with a fast positronium, and alternating fast positronium with slow positronium.
I mean, I think the question is about the big G measurement.
At the big G.
No, small g.
And then you can get rid of this external perturbation, which are also very small for positronium. Okay. Also for big G, but big G it's the same thing, basically. Okay. Thank you.
We have 2 announcements before the next talk.
Maybe you would visit
So let's take the speaker again.
Scusa, non era vero.
But only up to, let's say, 3 o'clock when we move to the other rooms, because then they will close. So we will move to these new Howl, which are essentially just at the entrance from First Umberto, but you can go all together there at the end of the lunch session. You have to go back to the Howl Octagonali and then go down the stairs, and then go up one stair.
If you stay behind this line, then you will not.
Coming from here.
So you want to have some time for questions?
It's an announcement by
5 minutes, maybe? Yeah. Okay. So then you would have 25, or if you want to have.
Thank you. So it's very quick. You may have realized that there on Friday there's a session that's called RQI General Assembly or something like that. This is not a restricted meeting. This is for everybody, and there's going to be some important announcements, and it's important. The participation of the community is important. Also, there's going to be a link to participate online. Perfect. So yeah, don't make plans. Come to that one too, please. Okay, I promise. Hopefully, it's going to be worth it. So, yeah, if you're thinking, no, I have a Friday afternoon free because there's this assembly. No, you don't have it free. All right.
Okay, so the final speaker of this morning session is Julia Gubitosi. She's actually, if I understand correctly, is going to tell us about another related cost action on the topic of bridging high and low energies in search of quantum gravity. So the topics are related. In fact, we already had a few weeks ago a joint workshop of working groups from the two cost actions. So, Julia?
Thank you. Thank you for the introduction. And yeah, so what I'm going to do today is to mention some topics of research that fall within this cost action and that are also relevant for this community. So let me start with describing what is the philosophy of this research program. Everything starts from the fact that since a few decades already, we are able to do phenomenology of quantum gravity, mostly thanks to early universe cosmology, astrophysics, and even gravity wave astronomy. When people realized that this was possible, it was a big breakthrough because it allowed to move quantum gravity from a purely theoretical endeavor to something that can be tested. And even more recently, as you very well know, there has been a lot of progress in tabletop experiments in quantum technologies, and this is also going to allow us to test some features of quantum gravity and gravity in quantum systems, as you have heard in very nice previous talks by Richard and Daniel. So what is the idea is that since now we are going to have soon access to observations, then we can really start to build models of quantum gravity that are not necessarily the full-fledged theory of quantum gravity, which is what people have been searching for a long time. But we can complement that kind of research with another kind of research where we build effective models for quantum gravity and models to describe the interplay between gravity and quantum systems. Now, in this talk, I'm going more to focus on the building of effective models of quantum gravity and their tests, because we have heard a lot about the other side, which is testing the interaction between gravity and quantum systems. What I want to emphasize is that all these approaches are really complementary and can really explore different regimes of quantum gravity. And by studying all of them, we can hopefully at some point understand something more about what quantum gravity is in its fullness. Just to make things a bit more concrete about what I mean. So let's consider this is the Bronstein cube where you have physical constants on the axis, and you can place one of the known or unknown theories in each of the corners. Ideally, when we are studying quantum gravity, we would like, this is not doing anything. Okay, we would like to describe the upper right corner of the cube. However, for phenomenological purposes and also to understand what is happening in that corner of the cube, it might be interesting to study some regimes which lie on the faces of the cube. For example, just two examples that are relevant for the rest of the talk, we may have that quantum gravity induces modifications of special relativity, of the relativistic kinematics of particles. And also we may have that gravity and quantum gravity in particular may induce modifications to the what I call no gravity quantum mechanics. So just closer. Thanks. I was seeing some waving. Okay, as you see here, we are not describing full quantum gravity, but we are describing deviations from what we know that are induced by quantum gravity. And this idea is what was at the base of the proposal for the bridge QG cost action, whose main aim is exactly to investigate what is at the interface between high energy quantum gravity and quantum gravity at low energies and the gravitational effects in quantum systems, with the ultimate goal to build a viable, phenomenologically viable theory of quantum gravity. Here I am listing some of our research questions, which you can read, and also how the cost action is organized in working groups. We have 2 high-energy working groups, theory and experiment, 2 low-energy working groups, theory and experiment, and then we have working group 5, which works exactly at the interplay between the high-energy and low-energy regime. So there is a lot of overlap with the RQI cost action, and I really hope that we will be able to do also some work together, as we have done in the workshop a few weeks ago. So let me now go to describe what kind of research I am thinking about, and to do so, I am going to use as a tool the non-commutative space-time. So for those of you who are not familiar with this, non-commutative space-time is a very old proposal that originally came from the idea that it could cure divergences in quantum field theory before we had the renormalization group. Then, of course, it faded out, but then it was revived in the 90s to encode the limitations that we expect to have in the possibility of localizing events because of quantum gravity, so because of the quantization of space-time. And recently, I mean, well, in fact, since the proposal as a model for quantum space-time came out, people have been also trying to investigate the relation of non-commutative space-time with other more fundamental, maybe quantum gravity theories. And in fact, at the moment, we have several indications that some kind of non-commutative space-time may emerge, for example, as a limit of loop quantum gravity, or we know that it emerges in some models of string theory, and also when we consider matter coupled to 2+1 quantum gravity. So it is a good model for describing some of the properties one might expect for a quantum space-time. And yeah, so before I go on, what I want to say is that also more recently we are starting to understand that not only non-commutative space-time may be a way to describe some quantum gravity effects, but also it may be emerging as some regime when you consider quantum reference frames. And this will be something I will discuss at the end of the talk. So it might be very nice because it might link in different ways quantum gravity and some theoretical tools that have been developed within quantum information community. So this is just to, first line is just to formalize the fact that if you have non-commutative space-time coordinates, then you expect some sort of uncertainty in the localizability of space-time points. And so usually, so this is the way you can describe, second line is how you can actually write the commutator between space-time coordinates. So we can write it as an expansion in the Planck length. So this is what you have at the center of the slide. But in the following, I will be focusing on what is probably one of the most studied models of non-commutative space-time in the context of research in quantum gravity, which is known as Kappa-Minkowski, where kappa is just the non-commutativity constant, which is expected to be related to the Planck scale. What is important is that once you are deforming, once you are introducing non-trivial commutators between space-time coordinates, if you want to retain covariance under relativistic symmetries, then you should expect that these symmetries are deformed. Otherwise, your commutator wouldn't be covariant. And to describe them, you use the tool of quantum groups and of algebras. Here I am showing the Hoff algebra of Kappa-Minkowski, so the Hoff algebra under which Kappa-Minkowski is covariant. You see that the commutators are nonlinear, and then you have non-trivial action on products of functions. This is just to give you the general flavor. So from here, what can we do? As I said, we can do several things. One thing is quantum mechanics on a non-commutative space-time. So what happens if you consider a plane wave? Coordinates are non-commutative, so the plane wave will be described by an ordered exponential. Then your deformed algebra of symmetries that I showed in the previous slide describes, for example, how momenta, when you consider multi-particle states, how you add momenta of several particles. And above all, what is really interesting is that you get a deformed time evolution of quantum system. How is this? So usually you write the time evolution of a density matrix via the commutator with the Hamiltonian. We are considering a free system, so no interaction with the environment. This commutator, in fact, when you are in the Hopf algebra setting, is called a quantum adjoint action, which depends on the form of your symmetry generators, so the ones that are described by the Hopf algebra. Introducing these into the time evolution of your matrix, it happens something really, well, it was surprising at first, but you get that the raw matrix evolves according to a Lindblad equation. It is surprising because there is no environment, nothing the system is interacting with. The fact that you have a Lindblad equation is just because you have this deformation of your symmetries, and in particular, a deformation of your time evolution operator. This means that you have decoherence. You can, for example, compute your decoherence time, and you see that it depends on your non-commutativity constant kappa. And something that is interesting is that because of the specific dependence of the Lindblad equation on momentum operators, so usually you see dependence on coordinates. Here you have dependence on momenta. Because of that, and because of the specific power of momenta that you have, you may deduce that you have a limit on the mass that a quantum system can have. So if a system has a mass that is larger than kappa, which is the Planck mass, then within this model, you would expect that the system undergoes decoherence really fast. So you wouldn't be able to observe it as quantum. So this is one thing. Then another aspect that we can study, so this was more in the low energy side. Another aspect that you can study is what happens in the high energy side. And here it turns out that if, again, you take the same model for non-commutative spacetime and deformed symmetries, you have effects in the behavior of relativistic particles. So imagine high energy particles coming from astrophysical observations. This happens because since the algebra of symmetries is deformed, for relativistic particles, you will have a deformation of the dispersion relation for a particle, which is what I wrote in the first equation. And because of that, you would expect that even for massless particles, higher energy particles travel at a speed that is different from the one of lower energy particles, instead of being always the speed of light, which is what you expect. And this means that if you observe high energy and low energy particles, you expect that were emitted at the same time from some source, they will arrive at you with some time difference, delta t. And this is something that we can, in fact, test in astrophysics. In astrophysics, the time difference depends also on the fact that we are in an expanding universe, so there is some redshift dependence. But in the end, what you want to see is whether there is a linear relation between the time of arrival difference between a very high energy particle and the low energy particle, and the energy of the high energy particle. And this, in principle, is a very small effect because it's suppressed by the Planck scale. So here I wrote it in terms of the Planck mass. However, because of the particles, if they are from an astrophysical source, are traveling from very far away, you expect to have something in principle visible. For example, if you have a 100 TeV particle, you might expect that it arrives with a time difference of even 1 day with respect to low energy particles for a source that is at redshift 1. So it can be quite a large effect. And you can study it. Well, it has been studied in many ways. What I want to describe here very briefly is you can look at high energy astrophysical neutrinos, which have energies of order 100 TeV exactly, and see whether you see a neutrino that is coming from the same location as a gamma ray burst, which is much lower energy, and coming from the same location, but with some time difference if you want to test for this effect. So you just compare the map of known neutrinos, the map of known gamma ray bursts, look at their time of arrival, and see if you see anything. And so if you do this, well, there aren't that many, even just spatial coincidences between these signals. But among them, in our last work, we were able to find 4 that lie within the range that you would expect if this effect was there. This might just be a chance. In fact, we computed what the significance of this is. It's not anything crazy at the moment, but it's enough to be interesting because we have a 0.57% probability that this is due by chance and there is no time delay effect in nature. Just very briefly, very recently, we observed the highest energy neutrino ever from the observatory KM3net. It was with energy of hundreds of PeV, so we are thousands of times more energy than what we used before. And we found that, in fact, this new neutrino is in very good directional coincidence with some gamma ray burst signal. A gamma ray burst that was observed in 2009. This neutrino was observed very recently, which, in fact, if you look at the plot where in the top right I added this new data point, could be reasonable within this effect. Again, this might just be a chance. The probability that that point would lie in the gray band if there was no effect is 1.5%, so it's still quite large, but it's interesting. The point of this was to show you that you can do phenomenology with these kind of models. So after showing you how you can study quantum spacetime, well, non-commutative spacetime at low energies, so for quantum systems, and at high energies using astrophysical observations, the last point I want to make is to show you that, in fact, studying this non-commutative spacetime may also lead to better understanding of the framework of quantum reference frames. In fact, what I'm going to tell you about in the following stems from discussions with Flaminia and Angel Ballesteros, where we were very interested because it seems that, so you have a quantum spacetime described by non-commutativity, but then also when you're looking at quantum reference frames, in some sense, you are defining a quantum spacetime because it is at the moment where your reference frame has quantum properties, then the way that you are describing transformations between observers, again, is not what you would expect in a smooth classical spacetime. So we were wondering whether there could be any relation between these two, in principle, very different notions of quantum spacetime. And to clarify this, we again used an approach where we studied the symmetries of these models, because symmetries are something more concrete than abstract spacetime. So let me tell you what we found before going to the details, so that in case I run out of time, you got the final message. So what we found is that, so if you look at quantum reference frame transformations between point-like particles, so in a quite simple model, you can close a group. And this is already something interesting. And then you ask, what kind of group is this group of symmetries that you can find within quantum reference frame transformations? And we found that this group of symmetries is, in fact, the first order of a quantum group described as in terms of algebra, so what I was discussing before. So it is as if these quantum reference frame transformations are a first order the formation of standard transformations in the direction of going to a full-fledged quantum group. And to show this, well, with this slide, many of you are probably quite familiar. Here you have 3 particles. One plays the role of a reference frame, and you want to look at how to transform to the reference frame of another quantum particle. And you define, for example, translation transformations and Galilean boost transformations that are described at the center of the slide. What does it mean to close a group? It means that you can combine many of these transformations, and you will always be describing a transformation that is already within your group. And in fact, this happens when you are using this 7-dimensional Lie algebra, where you have translation, boost, time evolution, and dilations. And these are all transformations that naturally emerge when you're looking at quantum reference frame transformations and ask that they are a symmetry of a free particle Hamiltonian. So here is the group structure that you want to compare to the quantum group structure. To do so, you take a quantum Galilei group. So before I was talking in general about quantum groups, here we want to look at the quantum Galilei group because these are Galilean transformations. And among all the possible quantum Galilei groups, you find one where the transformation parameters satisfy commutation relations that are close enough to the ones you expect from quantum reference frames. Let me just emphasize that in a quantum group, you have that the transformation parameters are non-commutative, and moreover, the commutators between the generators of your transformations are deformed with respect to the standard Galilean algebra that you all know. And these are the commutators that I wrote in the middle of the slide. So also here, to find the connection with the quantum reference frames, we represent the quantum Galilei group on 2 phase spaces that we name A and B, like just as we had the particles A and B in the quantum reference frame setting. And very interestingly, we find, so what is written in the center of the slide, that the general quantum Galilei transformation, if you consider it at the first order in the quantization parameter, which is this alpha that appears in all the commutators of the algebra and the transformation parameters, then the generic group element is the same as a quantum reference frame group element. In other words, quantum Galilei transformations are a linear combination of quantum reference frame transformations when you consider the quantum group at the first order. And even more interestingly, your quantum deformation parameter alpha is related to the inverse of the mass of the reference frame. So this is interesting because it's putting this relation between the 2 structures on a more firm ground. It gives you a physical interpretation of the quantum group quantization parameter. And I think I'm almost running out of time, and I want to leave some time for questions. So let me go to summary. So as I said, investigating non-commutative spacetime can be relevant for phenomenology of quantum gravity in several regimes, and also can help us link research in quantum gravity to research in quantum information and the investigation of gravitational interactions in quantum systems. I discussed one low energy and one high energy framework where we could use this non-commutative spacetime, as well as the link between the non-commutative spacetime and quantum reference frames. And I will end with an advertisement. We are having the annual conference of Bridge QG Cost Action in a few weeks in Paris. Unfortunately, we are at capacity for in-person participants, but you can still register for attending online in case you're interested, and this is the link to the website. Thank you for the attention. There is also a hand there. Okay.
Just a very quick announcement. This academy will close after lunch, so please bring everything with you while you're going.
Thank you for a very interesting talk. So, just to clarify if I understood it correctly, the last part when you compared quantum reference frames and this quantum group structure, do you have like a model which, like a non-commutative quantum mechanical or non-commutative quantum field theory, which has this quantum Galilei group as a symmetry?
So for the moment, no. We are taking the mathematical structure of the quantum group and see if we can link it to the mathematical structure of the quantum reference frame transformations. And through this, we also hope to find a physical model for these quantum groups. So we know that they describe non-commutative space-time, but this is a mathematical tool. Then you want to apply to some physical system, and this is yet to be done for this specific quantum group that we studied there. Okay.
Okay, thank you.
Thanks a lot for your very interesting talk.
Thanks.
Also on the last part, if I understood correctly, then you find this equivalence in the limit where the matter is mostly classical, like in coherent states?
Yes, so this is also something, so we find the correspondence between the quantum reference frame transformation and the first order in the quantum group. But on the other hand, this also allows us to clarify something about quantum reference frame transformations. And in fact, well, I don't have the details here because they wouldn't fit. But in fact, what we find is that all of this also implies that the state of the reference frame within the quantum reference frame framework is a semi-classical state, okay, or combination of semi-classical states. So the conjecture is that when we want to describe the reference frame as within a more general quantum state, so not a semi-classical state, then we would need to go beyond the first order in the quantum group description. This is a conjecture.
Thanks.